Hello.
Hello. Hello. Please start.
చేస్తాం కెమిస్ట్రీ ఐడి
कोणते दुपट्टे मी
बनवलाय तर टमाटो तर सांगा भाऊ. पार्टिसिपेट होता.
Hello. Hello. Hello.
मनोहर सर गुड मॉर्निंग.
Good morning. Good morning.
बस थोडं एक पार्टिसिपेंट इन्व्हाइट करून घेतो मग आपण वेळेवर सुरू करू.
Very good. Am I audible?
Yes sir, you are audible.
Vishal.
हो sir.
Vishal.
Yes sir.
During first session,
Yes.
I am going to share my screen.
Okay sir.
So that brief CVs of invited speakers will be displayed.
Okay sir, no problem.
Yeah.
आणि की ते पूर्ण भरली आहे कडू डांबूरवाली त्याच्या वरची टोकी पूर्ण भरली ते खोललो आता पावड्याला पहिले कडू वाली तिकडे
Hello, Vishal. Unmute.
हाँ.
Okay. Obanwar, sir. Please unmute from your side, sir. Huh?
Yes.
Okay. Thank you, sir.
हाँ. Rao sir, good morning.
Good morning.
How are you sir?
Good morning, sir.
Good. How are you?
Dr. Rao. Fine. How are you?
Good.
Very fine. I'm very happy that you are here.
I'm happy.
मूर्ती सर आले
मूर्ती पण नाही.
मोहरीला का
Vishal.
हाँ sir.
संजय ना?
Everybody is audible?
Yes sir.
Just check it.
Good morning, sir.
Good morning. How are you?
Good morning.
I'm fine. Yes, nice.
हॅलो. दिपेश झाला का तुम्ही रितेश कोड
नाही तुमच्याकडून ओपन काढून तुम्ही स्टार्ट व्हिडिओ करा ना.
कोकोडे सर आले.
संजू,
जी मालक.
गुड मॉर्निंग.
गुड मॉर्निंग.
तर इथे यांनी गाड्या पाठवल्या नाही अजून.
गाड्या रस्त्यात आहेत sir, रस्त्यात आहेत.
अरे,
नाश्ता संपलेला आहे.
vehicles are not reaching. We should start in time, no?
तर ब्रेकफास्ट.
हा बोला.
Because Dr. Rao, Dr. Pandey,
या.
hello,
Yes, sir.
Dr. Rao and Dr. Pandey, they are delivering their lectures close to midnight. This is to be remembered.
त्यांचं नाव कोणतं त्यांचं?
काय म्हणाला?
राऊतवाल्यांचं नाव काय? मला नाव काय त्यांचं? आरती राव ना? हॅलो. त्यांचं नाव
They may, because my name is there, full name is on the screen.
Yeah, right.
Maybe you should know that is R.P. Rao.
right. Exactly. Padmanabha.
Yeah,
Padmanabha is the name of Vishnu, no?
that's right.
Yes.
Padmanabha.
Sir, we visited that Padmanabha temple.
Oh, good.
Twice.
Good.
Yes.
Yeah, that's right. We were there, with the conference.
Yeah.
Yes.
Right.
Good.
Probably missed that conference.
Yeah.
हॅलो. हा, गुड मॉर्निंग. बोला ना.
गुड मॉर्निंग डॉक्टर. गुड मॉर्निंग सर.
Host has joined so late.
I was making the arrangement.
You were busy in making a transport arrangement, no?
सर कोकडे सर नमस्कार. कोकडे सर लक्ष नाही देतात. नमस्कार.
गुड मॉर्निंग राव सर.
Good morning. Good morning. How are you?
Already
morning,
130
sir.
participants join, huh?
Thank you sir. Good morning Rao sir. Yes sir.
Kokode is not audible.
I am not audible.
Unmute.
वा,
Morning
क्लिअर
sir.
दिसते एकदम.
Yes. Audible now. Am I audible?
यस
You
सर.
are not audible.
Not audible.
ऐसा कैसा हो गया?
Sir, good morning. Good morning, sir. Good morning. मी कसं ऑडिबल नाही.
ब्रेकफास्ट झाला का कोकोडे?
त्रास देऊन राहिलो.
आता आवाज निघाला.
गुड मॉर्निंग सर.
Shall we start? माझा आवाज येतोय का सर सगळ्यांना?
हो हो
Yes.
बिलकुल यू आर ऑडिएबल.
थँक्यू.
थोडा आवाज सगळ्यांना आवाज ऐकू येतो.
अरे सर
काय गुलाबजाम खाल्ले का सकाळी सकाळी?
हा बाप्पा विचारू कालपासून तो गोडच खाणं सुरू आहे त्याचं.
चाल मोरिल सर झाले ना जॉईन?
हा मोरे सर जॉईन झालेले आहे
हा.
आणि मूर्ती सर जॉईन झाले.
अरे वा व्हेरी गुड. चालते चालते. मोरिल सर
हा चेक करा मनोहर सर चेक करा.
हो. हॅलो हॅलो.
हॅलो.
हा मोरिल सर आता ऑडिओबल आहेत. मोरिल सर कॅन यू हिअर मी?
हॅलो.
मोरिल सर.
हा येस
सर सरांचं काही ऑडिओ येत नाहीये सरांचा.
बरं बरं पाच.
हा लावला आता लावला सरांनी. मोरिल सर.
गुड मॉर्निंग.
गुड मॉर्निंग सर. गुड मॉर्निंग.
गुड मॉर्निंग.
गुड मॉर्निंग.
Learn about this, okay, Rama? That's okay. Narun Bhatt.
Chandok has also joined Jabalpur.
Dr. R.P. Rao also seems to be there.
Yeah.
Yes.
Hello. Sir sir.
स्वाती.
Yeah, I can hear you.
Hello sir.
हा बोला.
Have you joined?
Present. Share screen.
Your presentation.
Presentation is here.
व्हिडिओ पण आहे समजलो का?
Shall we start?
Good morning, Dr. Rao.
लगेच पाठवतो. हॅलो, गुड मॉर्निंग प्रोफेसर पानसे.
मॉर्निंग, गुड मॉर्निंग सर. हाऊ आर यू सर?
या फाईन, ॲब्सोल्युटली.
iPad, whiteboard, desktop. देखा था?
राव सर.
Yes. Yes.
हा, डॉक्टर मोहरील सर इज सेइंग हॅलो, गुड मॉर्निंग.
Oh, hi, hello.
Very good
या
morning,
या
sir.
हा
प्रोफेसर
Nice
पानसे,
to
where
be-
is the air पुढे?
या
I don't know how to do that.
कल्याणकर सर आलेत का?
नाही, मोरी सरांना पोस्ट नाही केला.
Should come
नाही,
up
संजीव
with
संजीव म्हणून.
हॅलो.
संजीव SANJIV.
Yes. The presentation is visible on screen.
Yes.
Yes.
Very right.
Atul sir. Sir, Atul is not in the meeting right now.
विशाल.
हा सर.
आलेत का आपले कल्याणकर सर आलेत का?
नाही, त्यांचीच वाट पाहतोय सर.
अच्छा. फोन केला का त्यांना?
हो, फोन केला त्यांना. 5 मिनिटं देऊन द्या.
स्क्रीन शेअर काढून टाका.
पाठवलं तुमच्या मी. हो. मला थोडस व्हॉट्सअप करा. व्हॉट्सअप
सर कल्याणकर सर जॉईन झाले, दिसत नाही.
विशाल, मॅनेजमेंटचे लोक आलेत का?
हो सर, आलेत.
अच्छा,
ते रेडी आहेत.
रेडी आहेत.
हो.
हा, बरं झालं.
कालच ऍक्च्युली त्यांची भेट घेऊन त्यांना बरोबर टायमिंग सांगून दिलं.
व्हेरी गुड. कारण आपल्याला टाइमवरच चालू करावं लागेल बरं सगळं.
हो, कारण की वेळेची खूप आहे.
आणि टेक्निकल सेशन तर बिलकुल टाइमवर घ्यावं लागणार आहे आपल्याला.
बिलकुल.
Yes, it is already the time to begin.
Yes.
1 minute past.
9:30.
So 9:15.
9:16 झाले आता.
9:15 ला we were supposed to begin. I mean inaugural session.
कोकोडेने सांगितलं नसेल कल्याणकर सरांना बरोबर. US मध्ये आता ते जवळपास
रात्रीचे
10:30 झाले ना आता.
रात्रीचे
10, 10:30 वाजले असतील.
रात्रीचे 10.
सर नमस्कार.
10.
सर ते झाले सुरू. मॅडमचा फोन नाही लागत असेल. मॅडम जॉईन व्हायचे. वाट पाहत आहे सगळे.
चालू करू द्या.
हो सर.
विशाल.
पहिले आता कोकण संघ स्पीच होईल ना. त्याच्यानंतर मग यांचं घेऊन घे. ठीक आहे. त्याच्यानंतर मग कोण आहे पहिले तुझं अँकरिंग आता 9:15 झाला तर सुरू करू लागेल थोड्या वेळात.
हो, मला ते मग
झालं.
नाही घेतलं का स्क्रीनवर?
वाईट आहे मी पण हे फुल स्क्रीनवर येईल ना.
तिथून तुझ्यातून होते ना ते.
आता लगेच
सुरू करायचं काम ना.
हो ठीक आहे. तो आला नाही पण मीटिंगवर.
तो नाही का? नाही, तो याच्यात
विशाल आणि रितेश.
येणं म्हणा मीटिंगवर येणं.
रितेश किती स्मार्ट दिसतो.
नाही पण ते कसे मोबाईल वर बोलत असताना अनम्यूट करत नाही. म्यूट करत नाही. ऑडिओ आणि व्हिडिओ दोन्ही म्यूट करून टाकायला
दोन्ही सुरू
पाहिजे. त्याच्यामुळे काय चालू आहे हे सर्वांना समजतं ना.
सर त्यांनी बाकी लोक ट्रेन होतात ना.
हो.
पूर्व तयारी कशी करायची कॉन्फरन्सचा कोर्स वर काय.
पुढे
नाही सर काही घाबरू नका सर. आपला एक स्पीकर नाही आहे, प्रोफेसर आरोफ नाही आहे.
नाही आहे का?
हा त्यांची हेल्थ प्रॉब्लेम आहे, सगळे मेल आला त्यांचा.
बरं बरं बरं.
माझ्या सेशन मधले.
तुझ्या सेशन मध्ये
म्हणजे
मग तो अर्धा तास पहिल्या सेशनला
नाही 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 तो सगळ्या दिवसभर पुरवायचा आहे आपल्याला. दिवसभर पुरवायचा आहे तो.
हो बरोबर आहे. पहिल्या सेशनला जास्त वेळ लागतो.
ओमनवर सर मूर्ती सर आलेत का ऑनलाईन दिसत नाहीयेत?
अरे मूर्ती सर पण आले.
कारण बाकी सर्व गेस्ट आलेत, मूर्ती सरांची वाट आहे फक्त. मग आपण इनोव्हेशन स्टार्ट करू.
सरांना फोन लाव ना. लावू का?
सर जॉईन झाले का?
नाही सर, नाही झाले सर. गुड मॉर्निंग कन्व्हेनर.
अरे थांबून जरा बाबा.
142 participants have already joined.
करेक्ट.
वेगवेगळ्या ठिकाणी आहे सर ते.
Yes.
On Zoom 140.
Yes.
हा बोला. हा नाही तो ओमनवरचा करून आले. हा उचलला का फोन?
Yes, Professor, are you joining this inaugural function? Yeah, everybody is waiting for you, sir. Yeah, please join. Thank you.
रितेश फोटोग्राफर नाही आलाय?
सर बस येत आहे सर, रस्त्यात आहे तो. त्याला आताच फोन केला.
बरोबर.
Am I audible?
Yes, you are audible.
मूर्ती सर झाले का जॉईन बघ रे बा.
हो सर. अतुलला सांगा. अतुलला. वा 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 वा.
झाला?
आले
आला का अतुल? आला.
कल्याणकर सर झाली जॉईन? रितेश?
हा सर.
कल्याणकर सर झाली का जॉईन?
कल्याणकर सर एक सेकंड.
मूर्ती सर नाही झाले सर अजून.
आता जॉईन होतो म्हणाले ते.
बरोबर.
कल्याणकर सर जॉईन झाले असतील तर त्यांना समोरच्या स्क्रीनवर आणा.
नाही, कल्याणकर सर टेक्निकल प्रॉब्लेम मुळे जॉईन हो शकते. ही इज ट्राइंग.
अच्छा
बट नॉट सक्सेस. ही इज ट्राइंग.
विशाल
सिग्नल.
हॅलो विशाल.
हा सर बोला.
विशाल.
हा सर.
स्पॉटलाइट करून करायचं का फुल स्क्रीन? की अजून दुसरीकडे कुठे ऑप्शन नाही दिसत आहे?
एक मिनिट. वरती जा तुझ्या स्क्रीनवर.
हो.
राईट साईडला वरती नाही का गॅलरी व्ह्यू येतो.
ब्ल्यू कलरचा आयकॉन आहे.
हो तिथे त्याला कर. आता तुम्हाला फुल स्क्रीनवर दिसतंय.
दिसतोय मी?
हो.
आता?
हो आता फुल स्क्रीन दिसतोय तुम्हाला.
आता?
हो.
आया नाही.
तुझा एक काम कर, तू मला कॉल कर.
हा.
आता नसेल दिसत ना मी.
मूर्ती सरांना लिंक नाही पोहोचलाय.
हॅलो
सर व्हॉट्सअप करतो मी तुम्हाला डोळे सर, तुम्ही सेंड करून घ्या.
हो.
किंवा तुम्हाला जी केली आहे मी त्यांना शेअर करून घ्या.
अच्छा ती पाठवली.
विशाल.
हा.
आता नाही आहे मी स्क्रीनवर.
नाही तुम्हाला कॉल कर रितेश. कॉल कर.
ओके.
आणि चॅट बॉक्स जे आहे ना ते डिसेबल करून ठेवा, नाहीतर ती पॉपअप येत राहते विंडो सारखी चॅट मध्ये. त्यांना स्लाइड्स दाखवायला प्रॉब्लेम येतो मग.
चॅट बॉक्स
डिसेबल
करावं.
आणि मग डिस्कशनच्या वेळेला फक्त ती एनेबल करायची.
डिस्कशनच्या वेळेस.
हा विशाल
हाँ सर भेज दिया व्हाट्सएप पे।
क्या लिंक नहीं है क्या सर के पास?
नहीं हो रहे ज्वाइन हो रहे।
हाँ
भेज दिया उनको लिंक।
व्हाट्सएप पे क्यों भेजा है यार? मेल पे किया तो डायरेक्ट क्लिक करने के बाद ज्वाइन हो सकता। केमिस्ट्री डिपार्टमेंट कुठला आहे? नेवजाबाई हितकारणीचा आहे का? हा तिथला स्क्रीन येतो आहे आपल्याजवळ.
कल्याणकर सरांचा थोडासा प्रॉब्लेम हे जॉईनिंग तर इंजिनियर गेला आहे.
आपल्याला थांबायचं का तोपर्यंत?
कल्याणकर
सर सिक्वेन्स मध्ये भाषण आहे ना.
नाही मोहरील सर आहे अगोदर. 3 प्रिन्सिपल
सर मोहरील सर आहेत.
नंतर व्हीसी सर जॉईन होतील. तर शाल वी स्टार्ट.
उशिरा चालू झालं तरी चालतं ना.
शाल वी स्टार्ट.
आय थिंक सो.
सर येस सर स्टार्ट करू शकतो. रितेश
हा अतुल नाही आला अजून.
अतुल जॉईन नाही केलाय त्यांनी. तो ऑपरेट करतो आहे ऑनलाईन आहे.
हॅलो हॅलो
दिसतोय?
हो
टॉक आहे. आणि आता मीटिंग सुरू झालंय. मी रणदिवेला बोलवून घेतलं इथे. थोडंसं चेक करून द्या म्हटलं. तर टेक्निकली तुम्ही आम्हाला थोडंसं आजच्या दिवस स्टेबल. हां थँक्यू सर. हाँ सर. हाँ सुरू करू सर. हाँ मी बोरकरला.
मूर्ती सर हैज कम. वेलकम सर.
मूर्ती दादा नमस्कार.
वेलकम.
ठीक है.
मूर्ति सर गुड मॉर्निंग. कैन यू हियर मी?
उसका फोटो दिख रहा वो नहीं दिख रहे.
मूर्ति सर
फोटो नहीं है. लाइव है फोटो नहीं है. लाइव है.
चेहरा नहीं हिल रहा उनका.
नहीं हिलेगा वो देख रहे.
एक काम कर करना वेळ आहे.
हेलो मूर्ति सर.
मूर्ति सर देखता है नहीं.
मैसेज येतो है कि पीपल इंटर इन द वेटिंग रूम फॉर दिस मीटिंग.
ऍडमिट करून घ्या सर. ऍडमिट करून घ्या. आपण सगळे होस्ट आहोत.
सी वेटिंग रूम म्हटलं त्यांनी.
हा वेटिंग रूम मध्ये जाऊन त्यांच्या नावावर क्लिक केलं की
केलं. डन
ना.
हा यस.
ओके.
I am also admitting from here. All of you.
रितेश. Hello रितेश.
Murthy sir is okay. Murthy sir now this morning time.
Hello, Ritesh. Ritesh.
Murthy sir, good morning.
Hello.
Hello,
Hi.
Murthy sir.
अच्छा है
हाँ हेलो ना स्क्रीन से अरे आ रहा है ना यार नहीं हाँ आप दिख रहे हैं ना नहीं करो करो हो जाएगा मूर्ति सर का वॉइस का प्रॉब्लेम है बोलते मूर्ति सरांचा वॉइसचा प्रॉब्लेम आहे
अच्छा.
मूर्ति सरांचा वॉइसचा प्रॉब्लेम आहे रितेश
So very soon we are going to start this international conference on
Audible.
recent trends in advanced materials. Good morning, ladies and gentlemen. Am I audible to all of you?
yes
yes
The galaxy of intellectuals, Your Excellency, invited guests, teachers, and my dear friends. How different this morning is. Dear audience, you will yourself discover as the colors of International Conference on Recent Trends in Advanced Material 2020, ICR TAM 2020. It will be very soon unfold for all of you that has been jointly organized by Nevjabai Itkarni College, Brahmapuri District, Chandrapur, affiliated to Gondwana University, Gadchiroli, and led BS Arts Professor NG Science and AG Commerce College, Sakarkheda, District Buldana, Maharashtra, India, which one is affiliated to Sant Gadge Baba Amravati University, and also with Sri Sant Gadge Maharaj Mahavidyalaya Hingna, District Nagpur, affiliated to RTM Nagpur University, Nagpur. Well, my first and foremost duty on behalf of
चल काय बरोबर आहे हा
हो सर सर अनम्यूट केलं
Ritesh sir, unmute from your side, sir. Ritesh sir, unmute करा, unmute करा.
अनम्यूट कर म्हटलं तुझ्या साईड तुझा आवाज नाही येत. अनम्यूट कर तू.
So before proceeding, let me tell you about a brief introduction about this conference. In the view of great pleasure and initiatives by Government of India, especially the
तुम्हाला
and production. I heartily welcome all of you for this conference, as well as Honorable Vice Chancellor Dr. N.V. Kalyankar, eminent scientist Professor Mori, Chairman Professor KVR Murthy, Dr. Mourle, Professor Omanwar, Professor Doble, Professor Sahare, Professor Banpurkar, and all the resource person, Professor Rao, Professor Pandey, Professor Ode, Professor Arok, Professor Marta, Professor Mikita, Professor Diallo, Professor Justel, Professor Bob. In Zoom platform, around 2,646 participants and along with the international delegates are joining the conference from different countries. So not taking so much of your time, may I now request Dr. Anas Kokode sir to please convey his Principal NH College Brahmapuri. So with a great pleasure, we invite Dr. Anas Kokode sir on the online platform for his introductory remark to August gathering. I request him to present the brief agenda of this conference. Please, sir, Dr. Anas Kokode sir.
Myself, Dr. N.S. Kokode.
I request Dr. N.S. Kokode sir to please
am I audible?
come on online platform for his introductory remark.
Am I audible now?
Yes, sir.
Yes, sir. Yes.
Yes, sir.
Good morning. Myself, Dr. N.S. Kokode, Principal of Nevzabai Idkarni College,
सेंटर मध्ये आणा त्यांना
District Chandrapur.
सेंटर मध्ये आणा त्यांना पुढे सरांना
Have privilege to heartily welcome you all here for international conference. Recent trends on advanced materials on 6 July 2020 on online basis. I am proud to mention that the 11 international experts from USA, Africa, Turkey, Poland, Malaysia, Korea, and Germany are contributing online talks using the Zoom platform. Around 2,500 national and international delegates are joining the conference from various countries and all parts of our country, India. At the outset, I have privilege to heartily welcome Honorable Vice Chancellor Dr. N.V. Kalyankar, Gondwana University, Gadchiroli, eminent scientist Professor S.V. Chairman of the inaugural session, Professor K.V.R. Murthy, Registrar of Gondwana University, Dr. Ishwar Mohurle, Chairman of the various technical session, Professor Dr. S.K. Omanwar, Sant Gadge Baba Amravati University, Professor Sanjay Dhobale, RTM Nagpur University, Nagpur, Professor P.D. Sahare, Delhi University, Delhi, Professor Arun Banpurkar, Savitribai Phule, Pune University, and all the eminent international resource persons, Professor R.P. Rao, Professor Ravindra Pandey, Professor R.B. Pode, Professor Arov, Professor Marta, Professor Mikvita, Professor Dailo, Professor Justel, Professor Bod, Professor Sandeep, Professor Sriram Durjati. My best wishes to organizer, Principal Gawande, Principal Dr. Moglewar Man, and Convenor Dr. Sanjay Dobale, Dr. Atul Yerpude, Dr. Vishal Panse, Dr. Ritesh Kohde, and Organizing Secretary Dr. D.S. Gahane, Dr. Y.G. Maiwade, Dr. Gawande Ma'am, Dr. N.S. Dhobale Ma'am, Dr. R.S. National Migratory Committee and his team, Dr. Y.P. Kauri and his team as a technical committee. Nevzabai Bhaiya Hitkarni Education Society, Brahmapur, was established in 1941. Rashtra Sant Tukadoji Maharaj was the first president of this education society. Late Madan Gopalji Bhaiya was the founder and donated 150 acres of the land to this education society. NH College was established in the year of 1962. It embarked on the mission providing education to the backward, tribal, and deprived section of this area. NH College campus is spread up in 44 acres at Brahmapuri Taluka with constructed area about 16,000 square meter. The college is offering 21 programs across arts, science, and commerce, having with 10 research centers in subjects zoology, geography, physics, chemistry, botany, commerce, Marathi, English, economics, and history. Apart from running the UG programs in arts, science, and commerce, along with postgraduate in commerce on grant basis, college has started 10 PG program humanities in subjects like geography, economics, home economics, political science, sociology, history, Marathi, and MSc in four disciplines: physics, zoology, botany, and chemistry, BLib and MLib. The college has given the very remarkable facilities for the sports, NCC and NSS, and extracurricular activities.
Unmute, unmute, sir, unmute. You are mute now. Please unmute.
Okay, sir.
Okay.
Our college has the vision step in for the knowledge and reach out for service to the mankind. I hope you will have the good day ahead with gaining a lot of knowledge on recent trends in advanced materials deliberated by the experts. My best wishes to organizers and conveners for the success of this international conference. I am very much thankful to all the international resource persons and chairman for their contributions in the conference. Thank you very much. Once again, I welcome all the participants join this international conference. Thank you very much.
Thank you so much, sir, for sharing your views. That was really a remarkable introductory speech given by Honorable Dr. Anas Kokode, Principal, NH College, Brahmapuri. Ladies and gentlemen, uh, we rarely get this kind of opportunity to listen the words of wisdom. May I now request Honorable Dr. Nilesh Gawande, Chairman, Nehru Yuva Krida and Sanskritik Mandal Chikli, District Buldana, as well as the Principal led SB Arts, Professor NG Science and NG Commerce College, Sakarkeda, District Buldana. I request to play the video of Dr. Nilesh Gawande, sir, on the online platform. Please, sir.
आवाज नहीं तेज आवाज नहीं देता है आवाज नहीं था मतलब
Yes, sir. Yes, sir. I'm right. अरे आवाज नाही येत आहे लावले सरांचा रिप्ले कर
तेज काहीच नाही आवाज
म्यूट केला विशाल
आवाज येईल फक्त मग.
If it is not playing, skip it.
Yeah.
I think there are some technical issues.
Skip that.
For a while, we will skip that. Now, towards our next introductory speech, Honorable Principal Dr. Aarti Moglevar, Principal Sant Gadge Maharaj Mahavidyalaya, Hingna, one of the navigator of this flagship. I request the organizers to share her video and her thoughts about this conference. Please play Honorable Dr. Aarti Moglevar ma'am's speech on online platform.
Video है क्या?
Yes. Dr. Aarti Moglevar ma'am, Principal Sant Gadge Maharaj Mahavidyalaya.
हाँ सर. हाँ ना एक मिनट मैं बात करता हूँ.
आणि पेटंट निष्कर्ष आणि देशासमोरील होणाऱ्या विशिष्ट व्यावहारिक आणि विकासाच्या
It is not visible on the screen, please. The sound is coming only. Chemistry department.
जर्मनी येथील अग्रगण्य या कॉन्फरन्ससाठी या व्हायरस सारख्या
इनके मूर्ति सरांचे आवाज नहीं येत आहे.
ऑनलाईन पद्धतीचा
क्लिअर नाही होऊन राहिलं.
या कॉन्फरन्सच्या माध्यमातून आपले ज्ञान जगभरात 2000 प्रतिनिधी वेगवेगळ्या देशातून आणि आपल्या देशातील सर्व भागातून सहभागी मी नेवसाबाई हितकर्णी कॉलेज
आवाज येतो.
लेट बीएस आर्ट्स कॉलेज एजी सायन्स कॉलेज एजी कॉमर्स कॉलेज साखरखेडा यांना तसेच कॉन्फरन्ससाठी ज्यांनी वेगवेगळ्या पद्धतीची मदत केली त्या सर्व प्राध्यापकांचे व आयोजकांचे धन्यवाद मानते आणि तुम्हाला या कॉन्फरन्समधील जे काही ज्ञान आहे ते पुढच्या जीवनासाठी निश्चितच उपयोगी पडेल अशी आशा व्यक्त करते आणि माझी 2 शब्द संपवते.
Thank you very much, madam, for sharing your words of wisdom about the conference. Dear participants, let me tell you one technical issue that on the Zoom platform, either we can see the video or either we can hear the audio. By in the last speech, we had that problem. So we apologize for this technical issue. Dear participants, not a single event can be performed without a leader. It was a great opportunity for all teammates to perform under the guidance of Convenor, Professor H.J. Doble, Department of Physics, RTM Nagpur University, Nagpur. His efforts are marvelous and impart a new dimension in organizing this kind of events always. Not taking so much of your time, may I request Professor H.J. Doble on the online platform to deliver his convener speech, please. Dr. H.J. Doble, sir, to convey his convener speech.
Thank you, Ritesh, for inviting me. Good morning to all. Myself, Dr. Sanjay Doble, Professor, Department of Physics, RTM Nagpur University, Nagpur, India. Welcome you all in International Conference on Recent Trend in Advanced Material 2020. I pay my homage to late Professor B.T. Deshmukh, sir. He was pioneer of luminescence research in Vidarbha, part of Maharashtra in India. Honorable Dr. Kalyankar, sir, Vice Chancellor, Gondwana University, Gadchiroli, energetic and well-known personality, Dr. KVR Murthy, President, Luminescence Society of India. Professor S.V. Moril is my mentor. Sri Ashok Bhaiya, Secretary, Navjabai Hitkarni Education Society. Dr. Nilesh Gawande, Chairman, NYKSM Chikli. Sri Uday Moglewar, Secretary, Basheshwar Education Society, Nagpur. Principal of colleges, invited speaker, chairman, organizing secretary, and participants. As a convener of this conference, it is my duty to introduce detail and key point of this conference to all. Today, I am happy for organizing this big event with all three colleges. One is late BS Art Professor NG Science and AG Commerce College, Sakarkheda. Second college is Navjabai Hitkarni College, Brahmapuri. And third college is the Sri Sant Gadge Baba Maharaj Mahavidyalaya, Hingna. Some of the novel points in this conference, this is more important, and few great achievements of organizers are here. First novel point is, I'll just discuss here and share with all these participants and speaker also. This international conference is organized by three colleges from three different universities. First is the Navjabai Hitkarni College, Brahmapuri, from Gondwana University, Gadchiroli. Second college is the Sant Gadge Maharaj Mahavidyalaya, Himna, from the RTM Nagpur University, Nagpur. And third college is the BS Art Professor NG Science and AG Commerce. Commerce College, Sakarkheda. This is the Sant Gadge Baba Amravati University, Amravati. So all these three colleges from the three different universities. So this is that all this conference represented the combination of the whole Vidarbha and all educationalists combined together, and this is the represented this in this international conference. Second novel point is very important. All 11 speakers of this conference are international speakers. This is the great achievement of this conference. For a one-day conference, this indicates the organizer maintaining the relation at international level, and this is the best point for our research group or Vidarbha research student for collaborating work at the international level and to find position for postdoctoral fellow easily at a different place in the globe. And these speakers are Professor R.P. Rao sir from USA, Professor Ravindra Pandey sir, USA, Professor R.P. Pode from South Korea, Professor Abdul Arov, Malaysia, Professor Michaska Domaska Marta from Poland, Professor Douglas Mikutia from France, Professor Montou Delo from West Africa, Professor Thomas Justel from Germany, Professor Florent Bauer from Germany, and Professor Corinne Sengis, Turkey, and Professor Sita Ram Jati, New York, USA. So all these 11 speakers from the different part of the country, due to only for the one speaker, Professor Abdul Aro from Malaysia, he just received the mail. Due to the health problem, he is not participant in this conference as an invited speaker. Third novel point of this conference is again is important. Total registration of this conference is very tremendous, 2,645, and it may be around 3,000 within the 1 hour. So participant is cross the 3,000. It is the great achievement of this conference. All participants from the different part of the globe: Germany, Taiwan, France, South Africa, South Korea, UK, USA, Belgium, Italy, Greece, Poland, Turkey, Australia, Hong Kong, Russia, Israel, Egypt, Malaysia, Singapore, and so on. As well as to all the participants also from India also. In the different part of this India, just I'm mentioning some of the place important: Kolkata, Mumbai, Delhi, Amritsar, Bangalore, Tirupati, Kadapa, Gwalior, Indore, Bhopal, Hyderabad, Chandigarh, and Pune, Jammu, and Imphal. So all over India, also participants from all over India also participated in this conference. Again, is the fourth novel point is important. Again, I'm mentioning here, I'm one of the total 4 conveners for this conference. Total 4 conveners. I'm one of the one. The other 3 conveners are my PhD student, Dr. Atul Erpude, Dr. Ritesh Kode, and Dr. Vishal Panse, and all are extremely hardworking student, honest, and great researchers. So I'm very happy. This is the group is totally divided for this international event. Again, it is the one novel point is the maximum topic covered are cutting edge frontline topic presented by our respected invited speaker. So today is the young researcher or find all the very good interesting topic applied as well as to the theoretical. So all speakers cover the all topic from related to the material science in from the physics, chemistry, biology, electronics, and all this one. So this is the very important for the interdisciplinary work. And this topic is discussed here by the invited speaker. I think this is a very good platform for our all those participants as well as to the young researcher. I'm very grateful to all our chief guests for inaugural function, Honorable Dr. Kalyankar sir, Vice Chancellor, Gondwana University, Gadchiroli, energetic and well-known personality Dr. K.V.R. Murthy, President, Luminescence Society of India, and Professor S.V. Mohri sir, he is my mentor. For validity function, the chief guests are Principal N.S. Kokode sir. This is the main host of this conference, and due to his collaboration, this conference is possible. I'm especially thankful to the Principal Dr. N.S. Kokode sir, Dr. Mohri sir, Registrar, Gondwana University, Gadchiroli. I'm also thankful to all the college management member, principal for permission to organize this international conference and support us in all respect. Also, I thank all the international speakers, chairman, convener, organizing secretary, and organizing committee member for great support and active participation. So I'm very happy. This is the one of the train is start in this Vidarbha region in the center of the India, and this train is continue for the our young researcher. So our India is always good, doing the very good work with the collaboration with the international people, and I'm very thankful to all supporters. Thank you very much, sir. Ritesh.
Thank you very much, sir, for sharing your profound knowledge, thorough introduction about this conference with us. Your convener speech was full of zeal and valuable information, and you are always been a consistent source of inspiration for all of us young researchers in every aspect. So thank you once again for sharing your views.
Thank you.
Regarding this conference. Dear participants, now it's a moment to add the golden feather in the in this international conference. We are going to have the inaugurator of this conference, Dr. N.V. Kalyankar sir, Vice Chancellor, Gondwana University, Gadchiroli. So with the long list of his achievements and glory, I would like to invite Dr. N.V. Kalyankar sir, Vice Chancellor, Gondwana University, Gadchiroli, on the online platform for his most awaited inaugural speech. Please, sir, Dr. N.V. Kalyankar sir.
Hello, may I audible?
Yes, sir.
Okay. Sorry for joining the session late because of some technical issues. At the outset, let me good morning to one and all. That is the galaxy of scientists, researchers, and dear colleagues from the teaching fraternity. I am
main screen.
I am very happy.
Yes.
To be amongst all the material scientists because I belong also from the material science area. Recently, maybe slightly away from active research, but basically, I am a material science student, particularly working in laser physics and nonlinear optical studies of diatomic molecules. Let me first congratulate all three principals of the colleges, that is Dr. Kokode and his two other colleagues, principals, who have dared to have an international conference on a very interesting and very timely important topic, that is recent trends in advanced materials. Even though in a situation like this prevailing and increasing by lip and mouth, the COVID-19, this is the right time to be associated with each other and exchanging the ideas and the knowledge that we are having in our interesting field. A college which is located in my university, that is NH College, Brahmapuri, which is contributing lot in the areas of chemical sciences, physical sciences, and biological sciences. It's a big college and contributing much more research in the university jurisdiction area. Now I am not going to enlighten anything about the recent developments in the advanced material, but I want to quote certain things. How research helps in the well-being and in the evolution process of mankind, because we know that the discovery of metals in the evolution process had made a history in the development process. It has increased the development process multifold. And later on, invention of steam engine has also changed the world. And the inventions are very useful to the development and at the luxury at the cost to the mankind. Now we know that later on there was a milestone in the research areas of material sciences, that is the fourth state of matter, that is plasma. With the invention of this laser, high-end products have been brought in the research areas, and this is because of the technology that has proved to be identification of materials. Now we know that different instruments that we have developed, that is IPR, IC, that is gas chromatography, and later on different techniques for in the thin film technology and all. Another milestone was superconductivity, superconducting materials, which have brought this world very close, and today's outcome is the outcome that people across the globe are coming in contact with each other. They are coordinated, they are connected because of this research in the material science. Superconductors were the materials who have made a history in the development of the scientific era. And later on, the nanotechnological materials. These are useful in all walks of human life, not only in medicine, not only in agriculture, not only in defense, not only in other aspects. So, what are the different advances in material science? Nanotechnological materials have played a very important role in the application of drugs, particularly drugs for the cancer treatment and all. So I am sure that this conference, because just I was hearing from organizers that the scientists across the globes are taking part, well-known recent researchers in these advanced materials are going to deliver their lectures in their areas of interest. I'm damn sure that this will enrich the knowledge of our students, PG students, as well as the pioneer researchers in this area in the University Jurisdiction of Amravati, University Jurisdiction of Nagpur, and University Jurisdiction of Gondwana. Once again, let me congratulate Dr. Kokode, Dr. Botte, and others for organizing this conference. Once again, I will announce that this conference has been inaugurated, and my best wishes are with the organizers and the participants. Best luck to all. Thank you very much. Okay.
Thank you very much, sir, for sharing your deep knowledge about this conference with us. Your speech was really full of enthusiasm and valuable remark. We are fortunate to have you as an inaugurator of this conference. Thank you so much. The next distinguished honor us with his presence is the chief guest of today's conference, Professor S.V. Moril, Emeritus Scientist, RTM Nagpur University, Nagpur. With a long list of his achievements and glory, it will be a privilege for us to invite Professor S.V. Moril upon online platform to share his knowledgeable words in this international conference. Please, sir, Professor S.V. Moril, sir.
Good morning, friends. It's indeed a pleasure to be part of this international conference. We are very good at converting obstacles into opportunities. So you know that because of this pandemic, there was a sort of lull in holding the international symposia activities. But we have overcome that, and now we are having international conference at Brahmapuri. You know, holding an international conference. So all these international conferences were sort of monopolized by the cities which host international airports. So as to get the guests and the participants and so on. So I remember that one of today's speakers, Dr. R.P. Rao, he organized an international symposium in 1990 at Sekri Karaikudi. And he must still be remembering sort of efforts he had to make to organize it at a rather remote place like Karaikudi. And we also remember what sorts of efforts he made. In fact, another speaker, if I remember right, Dr. Pandey was also a speaker at that conference. And LSI was born during that conference. So during a meeting or sort of evening sessions of the conference, this idea was floated. And then thus was born Luminescence Society of India. So it was what I'm trying to point out is that it was very difficult in those days to hold an international conference at remote places. And today we are having international conference at a small town like Brahmapuri. So I feel really proud that the technology has enabled us, and technology has gone down to small places. And my grand students, they are making all the arrangements for this conference. And we are having all the international speakers. So I think we should not take much time. We are already late, maybe by 6-7 minutes. So I know all of us are eager to listen to them. So back to you, Ritesh.
Thank you so much, sir. This was a really amazing speech. Thank you, sir, for sharing your great knowledge with us. Ladies and gentlemen, we are fortunate enough to have the versatile personality, none other than Professor K.V.R. Murthy, President, Luminescence Society of India, Baroda, as the chairman of this conference. With an equal pleasure, I would like to welcome Professor K.V.R. Murthy upon online platform to add the glory in this atmosphere and to develop the skill of excellency. Please, sir, Professor K.V.R. Murthy, sir.
स्क्रीन वर आला ना सेंट्रल स्क्रीन वर आला सेंट्रल स्क्रीन वर आला
Yes, sir. Yes, sir. Yes.
KVR Murthy sir.
Murthy sir. Murthy sir, please unmute from your side and start your session.
Murthy sir, please. Murthy sir, okay.
ऑनलाईन आहे ना?
येत आहे.
हाँ मूर्ति सर अनम्यूट. नहीं अनम्यूट अनम्यूट. आपको कॉल किया गया है प्लीज. हाँ अभी आपको एंकर ने कॉल किया. प्लीज स्क्रीन पे आइए. ऑल आर वेटिंग फॉर यू. आ रहे हैं. यस सर.
Bring him in on main screen.
मेन स्क्रीन वर आहे.
आहे ना मूर्ती सर झाले.
त्याचं
AVR
कनेक्ट नाही
मूर्ती.
होऊन आता. साऊंड का अतुलला फोन करायला सांग ना. येत आहे येत आहे येत आहे.
Sir, you are not audible, sir. Sir. Sir, you are not audible, sir. Please unmute from your side, sir.
What's problem? क्या हो गया?
Sir, you are not audible. Please check from your side, sir.
सर ऑडिबल नहीं है ना. अनम्यूट करो ना. हाँ अच्छा फोन का आवाज आ रहा है क्या? फोन पे बोलेंगे. हाँ हाँ अब फोन कनेक्ट हो सकता है. रितेश फोन कनेक्ट हो सकता है.
There are some technical
आवाज नहीं आ रहा
issues
उनका.
for the speech of Professor Xavier.
उनका साउंड का प्रॉब्लेम है. साउंड का.
ठीक आहे पाहू चेक करून पाहू सर. त्यांचं तिकडनं त्यांनी हे केलं ना.
नहीं उनको आवाज ही नहीं जा रहा. आवाज नहीं जा रहा. आ रहा कुछ नहीं. 1 मिनट सर 1 मिनट. प्रॉब्लम क्या है? या just he is trying sir. He's trying to connect you. Don't worry. 1 minute please. Yeah.
त्यांचा मोबाईल तर लॅपटॉप घेऊन ठेवला तुम्ही.
मोबाईलवर होतं का? मोबाईलवर कनेक्ट करायचं का त्यांना?
क्लिक कर म्हणा. सर चालेल. त्यांनी जर का कॉल केला तर चालेल सर.
अच्छा अतुलला कॉल करायला लावू?
हो चालेल सर. हो मी सांगतो सर. मी अतुलला सांगतो.
हाँ अतुलला सांग सरांना फोन कर मला.
I think we have some.
येत आहे रितेश येत आहे. फोनवर येत आहे.
Okay.
अतुल त्यांना फोन करतो. फोननी आवाज येतो. अतुल
सर कोकोडी सर बोलत आहेत त्यांच्यासोबत.
हाँ मालक नमस्कार. बोला ना.
माझं पण आम्ही त्यांना फोन करतो त्याला
शेअर स्क्रीन करा पुन्हा. Share screen.
Hello, can I speak?
Yes, sir. Yes,
Yeah,
sir.
yes, sir. Yeah.
Yeah. Good morning to everybody. So, my society members and other participants, I'm happy to be part of this event organized by Dr. Alex Bokle, in support of his my friend, Sanjay Doble. The material science. The material science is never ending program. Very time. There we need more and more material. So the global society of material scientists, the material scientists basically are chemistry, chemical engineers, metallurgists, all together form the material science, a group of material scientists. Their goal is to give a proper material for a particular device application used by the doctors or agricultural scientists or electrical electronic engineers, mechanical engineers. This program includes so many lectures. So few are from our Lumen Science, and I see that the class is on the line last half an hour to give his talk. So already today his time is on pictures, 10:30 night at California. So with this I stop. I congratulate the company and the team for the arrangement of the program. Thank you very much.
Thank you. Ritesh, continue.
Thank you, sir. Thank you so much for your address. It was full of passion and priceless as usual. So, I think now we should move towards the technical sessions. Ladies and gentlemen.
The campus is, and this reminds me again from Sagar, because Sagar also has a big lake where I grew up. This campus is fall colors, but Michigan is a little bit colder than California, where Dr. Rao comes from. So for fun, the students make statues here. And because our snowfall is about 200 inches, and they for fun, they make these sort of sculptures to entertain themselves.
Very nice.
Thanks again.
Thank you. Am I audible now?
Yeah.
Yeah. I'm very much thankful to both speakers, rather, R.P. Rao sir and Pandey sir, who were kind enough to spare their valuable time for this particular event. I am very much delighted to have a presentation which is being given by Dr. Ravi Pandey sir, that he has motivated people. He has motivated people to go for predictions first and then designing. So simulation initiates predictions, and then one should design accordingly so that we can have a better products for future generation, and that is what the innovativeness. I am very much thankful to Dr. R.P. Rao and Ravi Pandey sir. Because of some technical problem, I could not display and speak on their achievements. Both the speakers have achieved a lot in luminescence field, and they have developed their career not only in India, but they have lightened a lamp in the world as well. One is a medicinal applications, and other is the predictions and practically designed materials. And now I go for the third speaker of the day, And the third speaker of the day is Dr. R.B. Pode. Dr.
So,
R.B.
Omanwarji,
Pode.
just a minute.
Yes.
1 minute.
Yeah.
So
Please.
the participants, if you have any questions about the modeling or simulation, feel free to write to me, and I can get sort of guide you, because we have a lot of software packages which are freely available.
Yes.
In that sense. So don't hesitate.
Thank you so much, sir.
Send me email. Thanks.
Yeah,
And
yeah,
good
yeah.
night.
Very nice, very nice. So kind of you, sir.
Sure.
And very much thankful to you for providing your everything. I may now invite Professor R.B. Pode, sir. Who is a professor at Department of Kyungju University, Seoul campus, and Dr. Pode is currently working as a professor in the Department of Physics, Kyungju University, South Korea. His research interests include experimental condensed matter physics. He is serving as an editorial member and reviewer of several international reputed journals. Dr. Pode is the member of many international affiliations. He has successfully completed his administrative responsibilities at his institutes as well. He has authored many of research articles and books related to experimental condensed matter physics. Earlier worked at the Nagpur University in India as a faculty till 2007, and he has guided several postdoctoral students as well. Then awarded PhD degree to more than 10 students under his supervision. He delivered several invited talks and special lecture series on OLEDs and both international and national level. He has authored more than 100 publications in the reputed international journals and proceedings. Recently, he has created the Clean Energy Research and Information Center to disseminate the information and knowledge about the clean energy. And he particularly for 10 years, he worked more than 6 years, he worked at ICT Petri State in a postdoctoral fellowships consistently from 1999 to 2004 and 2005 to 6 Brain Pull co-first visiting scientist in Korea. Today, since Dr. Pode belongs to the Department of Physics, Nagpur City, Nagpur, he was a torch bearer for all of us, including me, and he has inspired many students at Department of Physics, Nagpur City, Nagpur. Today, he will be presenting his work on OLEDs, current and applications. On the behalf of the organizers, I am very much happy to invite Dr. R.B. Pode, Ramchandra Pode, to start his presentation. Thank you.
Thank you very much, Dr. Omanwar, Dr. Kokode, and other organizing member. In fact, I was reluctant. Can you hear me?
Yes, yeah, everybody.
In fact, I was reluctant. Can you see the screen?
Yes, sir. Yes, sir.
So I was reluctant to participate in the conference, being in the last week of the semester. But in fact, it is difficult for me to say no to Dr. Omanwar and Dr. Kokade. So I plan a very simple lecture, and that is about the organic light emitting diode devices, current status and applications. So I have planned this lecture in two parts. First part is a general introduction to the organic light emitting diode devices, and the second part is mostly applications. So this is our university. You can look at this is the main building of the university, and I directly go to the lecture. So if you look at in this slide, the electroluminescence in semiconducting material. started with the electroluminescence in inorganic semiconductor, silicon carbide, long back about 100 years before, and later on for 40 to 50 years, not much was done in this field, and then later on, in 1950, the electroluminescence in organic material was demonstrated in 1950, and subsequently in 1963, the electroluminescence in anthracene crystal was demonstrated, and first OLED was also demonstrated around 1962, but the efficiency was very poor. Also in 1977, thin film, the luminescence in organic thin film was demonstrated, but the efficiency was not so high. So later on, subsequently, for 10 years, nothing was done. And then a device consisting of a multi-layer, more than one layer, so was demonstrated in 1987 by a people, scientist working in Eastman Kodak company. And later on, at the same time, this, the 1987, the luminescence was in a small molecular organic materials. Later on, the 1990, the luminescence, the electroluminescence in polymer was demonstrated at the Cambridge University. Both are used as a organic light emitting diode. And then in 2000, the luminescence in flexible organic light emitting devices demonstrated. Also, the phosphorescence OLED demonstrated at the Princeton University, the efficiency much improved. And later on in 2012, the TADF, a thermally activated delayed luminescence materials were invented by Japanese people. So if you look at in the next slide, the first device in 1965 was only one layer and two electrodes. One is the cathode electrode and one is the anode electrode, and that was demonstrated in a crystal. The efficiency was very poor, not useful for making any commercial devices. And later on, as I mentioned, in 1985, instead of one layer, they use two layers. This is the emitting layer, EML, and the second layer is the hole transport layer, to increase the efficiency of the hole injection into this emitting layer. So the efficiency is much improved, and later on, in doped, the emitting layer was doped with this a dopant material, and the efficiency is still improved. And then subsequently, a multi-layer devices, the organic light emitting devices was demonstrated, and here the efficiency of the emission is very improved. And later on, this is the doped transport layer. So here we have to improve the efficiency of this whole transport dope layer, as well as a electron transport dope materials. So the efficiency is very improved, and you can make a commercial device using this last pin structure. As I mentioned, the organic materials consist of carbon and hydrogen atoms. So if you look at the hydrogen atom, this is a single carbon atom. In single carbon atom, we have four valence electron, and this first three, 2s, 2px, and 2py, these three electrons form a hybrid orbital, atomic orbital, and then 2pz form another p orbital. And if this carbon atom, here you see the bonding of the carbon atom, chemical bonding of the carbon atom, and sp2 hybrid bonded with this the head-on bonding with the another sp2 of the another carbon atom, and here we have a side-on bonding. This side-on bonding form a pi bond, and here this form a sigma bond. And this pi bond, this form, if you look at this energy level, this is the pi bond, this is pi 1, pi 2, sigma 1, sigma 2. Here we have 4 electron. So here this 1 electron of this sp2 hybrid participate in the bonding with this 1 electron of the sp2 hybrid of the another carbon atom. So we have 2 electrons here and 2 electrons of pz orbitals. So we have 4 electrons. So how many atomic orbital? 4 atomic orbitals. So we get a 4 molecular orbitals. So these are the sigma 1, pi 2, sigma 2. These are the molecular orbital formation. And then the sigma 1 molecular orbital is fully occupied. This is pi 1 is also fully occupied. So this form a highest occupied molecular orbital. Which one? This one, pi 1. And then this pi 2 and sigma 2 star, these are the empty molecular orbitals. So here, if you look at in the figure D, here I have shown that the highest occupied molecular orbital are completely filled, and the lowest unoccupied molecular orbital, these are empty. So this is just like a valence band in the inorganic semiconductor, and LUMO is like a conduction band in the inorganic semiconductor. So whenever there is a transition from this HOMO to LUMO, so you get this 1 electron goes to this LUMO, and this has a spin half. The total spin of the system is 0. So this form a singlet state, and if the spin half plus spin half, this form a triplet state. So singlet, triplet state are very important in organic materials. And in the next slide, if you see the device structure, how the device structure is manufactured. So it started with the ITO. ITO is the anode electrode deposited on the glass substrate, and on this we have a one layer, the hole injection layer, and then subsequently we have a hole transport layer, and then we have a emitting layer. Similarly, here we have a electron injection layer, because why this we need electron injection layer is because of the cathode Fermi energy, and this LUMO, the conduction band in the organic, this energy gap is very high. So the barrier is very high, so electron cannot go to this LUMO. So we need electron movement from this cathode to LUMO and LUMO. And then whole move from the HOMO to HOMO, and then reach to this emitting layer. And in the emitting layer, the exciton is formed. The combination of the positive charge holes and negatively charged electrons, they form exciton in this emitting layer, and the recombination of the charges in the emitting layer, in the exciton, you get a light emission. So this is the simple emission principle of the organic light emitting diode. And in the subsequent slide, so how these are classified? These are classified, the organic light emitting diodes are classified according to several configuration. So one is the classification based on the emitting material, whether the emitting material is a low molecular emitting material, small molecular weight emitting material, or the polymer molecular material. Polymers, as you know, these are the molecular weight is very high. So these are classified according to these configuration. And the second configuration is according to light emitting structure, whether light emission is from the bottom electrode, anode, or the top electrode, cathode, we get a bottom emission or the top emission. The transparent OLED is the emission from the both side, as well as bottom as well as the top side. And in the inverted OLED, the cathode is at the bottom and the anode is at the top. So we have 4 types of the diodes according to the classification of the emitting structure. And finally, we have a emission, the classification of the OLED according to the emission mechanism. So we have a fluorescence OLED, phosphorescence OLED, as well as the thermally activated delayed fluorescence emission, and the latest is the hyperfluorescence emission OLED. I will explain what is the importance of fluorescence, phosphorescence, and TADF emission, what is the difference between these two. So this is a simple block diagram of the bottom emission. The light output is collected at the bottom electrode, and here the light is collected at the top electrode, from the cathode electrode. So this is a simple configuration. It looks simple, but when you make a device, it is not a simple. So in this device, you see the light emission from the top electrode, cathode electrode, as well as a bottom electrode. So we have a reflective anode. So this is a partially reflection, not a complete reflection. So some light is transmitted through this anode, and here the light is transmitted from the second electrode, that is the cathode electrode, and is collected from this the top side. As I mentioned, in the inverted OLED, the cathode electrode is at the bottom, and the top electrode is at the top electrode is the anode. So this is the conventional OLED. This is the conventional OLED where the anode is at the bottom. But in this inverted OLED, the cathode is at the bottom and the anode is at the top. The light is collected from the bottom. So here, this is also a inverted OLED, but the light is collected from the top inverted OLED. This is the bottom inverted OLED. The advantage of this, the inverted, is used in the active matrix OLED devices. So mostly used for the display applications. So I will show you later on this slide. So in this, if you look at in this slide, you will see the evolution of the OLED devices. So as I mentioned, in 1987, the device, this was invented by the Kodak people, 1987, and this was based on the small molecular organic material, and the emission is the fluorescence emission. I will explain what is the meaning of fluorescence emission. And then the second generation, here efficiency is not very high in the first generation. So to improve the efficiency, phosphorescence organic light emitting devices were demonstrated. Here efficiency of the light emission is 100%. And here the later on, the TADF material, the thermally activated delayed fluorescence, the devices were invented in 2012. So this is the third generation, and the fourth generation, this is the latest, is this is in 2014. So their efficiency is improved. Also, the color purity is also improved. The emission spectrum become very narrow. The half width is very, very narrow. So if you look at in this slide, so this is the first generation, the organic light emitting devices based on the fluorescence emission. So here, this is the singlet energy level. This is the triplet energy level. So you see the singlet triplet energy gap is very high, and this singlet to singlet energy, this is the allowed spin transition, because here spin is not changed. The triplet total spin is 1. Here the singlet, the ground state is 0, spin is 0. So here these are not spin allowed transition. Triplet to singlet, not spin allowed transition. So you get the emission from the singlet to singlet emission. This is the fluorescence emission, and you get only 25% of the emission efficiency. And later on, a new materials. So these are the phosphorescence material. These are mostly doped material, and these are doped with the iridium complexes as well as platinum complexes, the high atomic material, high atomic weight materials. And here the singlet to triplet S1 to T1 energy gap is very, very low. So sometimes electrons stay in the triplet state, sometimes go to singlet state. So this the intersystem crossing is allowed here, and you get the emission from this triplet state. So here singlet state, triplet state, they are intermixed. So you get the emission from this triplet to S0 singlet state. So you get emission from all these 4 electrons. So the emission efficiency is 100% emission efficiency. And in this case, thermally activated delayed fluorescence, this gap, the singlet triplet gap is even smaller than this fluorescence emission. So here, this electrons in the triplet state, T1 state, again go back to the singlet S1 state by the reverse intersystem crossing, and you get the emission from the singlet state to a singlet state. And here the efficiency is 100%, as well as the quality of the spectra is very much improved. And if you look at in this slide, the emission spectra of the TADF material. So if you look at here, the half width of this TADF, this is the blue, and this is a faint line is the fluorescence emission. The half width is very large, and here half width is very narrow. There is no intermixing of green color and blue color and red color. They are all well separated. So you get a very, very pure spectrum in this TADF emission. And later on also in this, the hyperfluorescence emission, the efficiency is very, very much improved. Very, very much improved. So you look at here, the final emission is from the fluorescence. The final emission is from the S1 state, fluorescence state. So if you look at in this, okay, in this figure, how we get, this is the TADF. The hyperfluorescence emission is doubly doped the emitting material. So this S1 is the host material. This is doped with the TADF material, and again doped with the fluorescence emitter. And the final emission is from the fluorescence emission. So the efficiency is very much improved. And these devices, these are the latest devices. These are very, very important devices. Most of the commercial application nowadays are based on the flexible OLED devices, and the future applications will also be based on the flexible devices. Flexible devices nowadays are very hot devices, popular devices. So you can have a lot of applications on these devices. Here, all these materials are flexible. The flexible passivation, flexible cathode, flexible anode, and also a flexible substrate. So you can bend this device, you can fold this device like this. So these are very, very important devices and lot of applications. So you can bend this device. If you look at here, this is the outward bending state. So you can bend like this, and this is the inward bending state. So we have two bending, inward bending and outward bending. So here the bending diameter is 30 millimeter, and here the bending diameter is 10 millimeter. So, and as I showed in the previous slide, that all these substrate, all these materials in the flexible devices are a flexible. We have to use a flexible substrate. So flexible substrate may be in the form of plastic, thin metal foil, or a flexible glass, a thin glass. So the substrate must be thin, lightweight, transparent, as well as the substrate surface must be smooth. It should have a good flexibility and also have a thermal durability. so it should withstand a higher temperature. The electrode must be flexible. The electrodes may be a metal or alloy of the metal or others. So for a cathode, for example, cathode, the cathodes are the transparent conducting oxide or a metal thin film or various metallic alloys. And the anode may be a silver nanowires, or this is a organic conducting layer P dot, or it may be a metal mesh or a graphene or a carbon nanotube. So you can use anything. And encapsulation in organic devices is very, very important, because the organic materials are susceptible to a moisture and oxygen. So you need to protect the organic materials, organic devices. So you need to have a encapsulation. So encapsulation may be a multi-layer encapsulation like this, or a packing encapsulation using a PDMS polymer and or dielectric stack hermetic sealing, or a flexible encapsulation using a inorganic and organic layers. So as mentioned in the previous slide, so you need to protect a organic devices. If the organic devices are not protected, so the device will die within a few hours. So you see, these are the dark spot, the moisture, because of the moisture or the oxygen that penetrate into the devices. So you need to protect the devices, and device will finish within this much time. So here I have shown a device, this yellow color device finish in 283 hours. This is protected, and this is 84 hours not protected. So you need to have a very good protection, a passivation of the devices. So this is a second part of the lecture. As I mentioned, the organics, they have a lot of application. They have a application. Now you will see, I will show you, these can be used to have a television or a monitor from flat surface to a curved panel TV. Or you can have a OLED TV in the form of wallpaper. You can fold it. A small organic molecular display can be used in the smartphone. Nowadays, you see all the smartphone, a latest smartphone, are they are using a organic displays. Tablet also are using a organic display, and many handheld digital devices, they use organic display. So these applications, display applications, already well commercialized, and these are the wearables. So where we can use for the OLED light sources into a fitness band. I will show you this, where you can use a Apple Watch, you can use in Samsung band, you can use Fitbit's this band. So these are for a wearable devices. You can use this is a small organic display. And later on, this the fourth application is in the lighting panel. So these may be a future applications. Currently, it is not well commercialized, but it is on the way of commercialization. This the lighting panels. So this is a emerging market, and mostly the flexible and homogeneous panels, they may find applications in this the lighting panel. And the most recent and future applications are the OLED micro displays, which have a exceptional refresh rate and a reduced brightness level, and can be integrated in many devices. So these are the future OLED micro display. These are the future application. So in this, you will see we started this TV started with the cathode ray tube display, later on improved with this the plasma display, second generation, and third generation is the liquid crystal display, and this is the fourth generation, that is the next generation is the OLED display, but it is not affordable. The cost is very, very high, more than $2,000, even maybe more. So it is not very popular OLED TV. So, but in future you may find a TV. But recently, many this thing companies, they are bringing a organic TV. So if you look at here, this is the LG OLED TV. I don't know whether this model is available in the market, Indian market or not, but you can find on this the here somewhere. And this is the TV. This is the 85-inch OLED TV, and demonstrated by the Sony. And also this is a Japanese company, Sharp. This is 55-inch and 65-inch. This is the based also active matrix or organic displays. And this is also a Japanese company. So mostly Japanese companies are in the forefront in the development of this TV, OLED TV. And this is this TV, Vizio. This is the Chinese company. Many are not aware. This Chinese have taken this the OLED research about 10, 15 years before. They were nowhere in 2006, 2005, but they captured very fast this field, the organic light emitting devices, and they have now may take over the Korea also, this field. So this is the Xiaomi OLED TV, latest, recent, this just few days before they launched this TV, 65-inch OLED TV, few days before, not even a month. So these are the application for a bigger display, and these are the application for a smaller display. This Apple iPhone 12 may not be in the market, may come this year or next year, but they are likely to use a this 6.1-inch OLED TV, OLED display. This, and this is also these are already using the Samsung. They are using a small display. So this is one. This is one application. And Huawei phone. These they are using this active matrix OLED display, and the cost of this Huawei is much lower than the Samsung and this the iPhone. So many people may buy this thing, the Huawei. And also Xiaomi, Redmi, they also recently launched this, the organic smartphone display. So they are using now, they already in the market. These are the applications, a wearable devices. If you see, this is the Apple Watch, this is the Samsung Watch, and this is the Fitbit Xiaomi MI band. So they are using a small organic OLED displays. And in this slide, you see this is the recent Samsung foldable smartphone they use. This is a foldable. Maybe this foldable phone is available, recently launched in the Indian market, but the cost is more than lakh. So maybe 1.2 lakh. So it is very costly. So this is available also in the Indian market, and they use a organic active matrix organic display. This tablet they use the organic display, and this is a Royal is the Chinese company. They are making a flexible. If you go to website of this Royal Chinese company, you will see lot of flexible displays, a third generation flexible display developed by this company. And this is the iPhone, foldable iPhone. It is not available, not at launch, may come latter half of this year. And this is the Lenovo foldable phone. So this is Huawei also launched a foldable phone, and this Omnidia, also TCL. This is also a Chinese company. These phones are available in the market. They are all using a organic devices, display devices. And the next application is the lighting application. This is already demonstrated by the LG. This is a LG lighting panel they have installed somewhere in Seoul. They have also demonstrated this type of lighting panel. These are the application, and this is the lighting panel, a flexible lighting panel demonstrated by the Fraunhofer. Several applications, you can find a flexible as well as rigid lighting panel. Several you can make a devices. This is possible with the only organic devices, flexible and a rigid. So you will find a lot of commercial applications of this. The organic lighting panels are like this. Outdoor application, it can be used in architectural design, and it can use in a, you see this, a OLED, this OLED fanciful design. You can use this. So you can make this is a OLED device. You can make this. You can use in a hospitality sector. You can use anywhere. Several application, and this may be a future application. The future application of the OLED lighting. This is the internet of the lighting things. So you can connect all this lighting, OLED lighting devices to through this wireless circuit to a router and internet cloud, and you can control by a sensor, smartphone, tablet. You can control all this. So this is the smart lighting. These are the future applications of the lighting. And this already some automobile companies, they are using a OLED devices as a display as well as lighting.
Time is.
So here,
Please observe time. You have to observe time. 5 minutes only.
Oh, almost finished.
Yes, sir. Yes,
Almost finished. So you can look at in this the organic display. It can be used for the display. You can see the rear side, and here this is used for a tail light. So you can see several applications of the OLED in the navigation display. And as I mentioned, the OLED micro display, these are used in a augmented reality and virtual reality. So you must have heard a Google Glass. So you can project a image near to eye, or you can have a projection to the head-up display. The display used is a micro display. Micro display in this 1 inch, a small area, the pixel density is very, very high, very, very high. So you can use this as a micro display. These are the future applications. So there are several applications, and many companies are involved in this micro display applications. So you can see in this slide, many Chinese companies, Korean companies, Japanese, Taiwanese companies, Europe, and US companies, they are involved in these micro display applications. These are the future applications. So as I mentioned, this this talk is very simple. I have almost finished. Thank you, Dr. Romanwar, for giving me an opportunity to present my talk. So thank you very much.
Thank you very much, sir.
Thank you very much, sir.
Presentation. And sir,
yes,
it is a real thing that you have inspired many youngsters for getting into the OLEDs and the active research. You set an example for the people in Vidarbha that you can do any challenging job if you work for. So it is just because of your hard work you could achieve those things. I am very much thankful to Dr. Pune sir for accepting our invitation, and as well as he has delivered a very nice talk on OLED. He has also talked about the augmented reality and virtual reality. I think that is the future for online learning. Softwares are being developed and it will be developed on the basis of augmented and virtual reality. And these OLEDs applications are there for micro displays. So micro displays plays very important role in getting the information in packed in very small square area, and that is what the applications are. I'm very much thankful to all of my speakers for these sessions. The first technical session, we could have eminent scientists from all begins from R, as I have said, R.P. Rao, who is the president of Incorporation presently, and he has got many awards to his credit. He has accepted our invitation. During his 45 years of career, Dr. has over 100 publications, 2 books, book chapters, patents and patent applications 19, and he has been decorated by many awards like the SID Special Recognition Award. He is a recipient of Albert Nelson Lifetime Achievement Award, SID Chapter Service Award, and so on and so forth. And he talked on first for materials and practical applications. He has inspired youngsters to go for practical applications and how one can have medical applications by the luminescent materials. The second speaker, Dr. Ravi Pandey, he has inspired people he has inspired new generation for going into simulation, do predictions, and do creative products. And with a very simple slide presentation, he has motivated people. He is from Vidarbha region. Second speaker and third speaker is also from the Vidarbha region. He obtained all, Ravi Pandey sir has obtained all degrees from the BSc and MSc degrees from Saga University, did a PhD in Canada, and joined Michigan University in 89 to 94 as assistant professor, and then he raised to 98 as professor and now chair. He has got many postdoc fellowships for which our students can go with him. And he has also awarded many awards and presented lucidly on synthesis, characterization, applications of carbon-based nanostructure. And the third speaker of the day, our talk speaker, Dr. R.B. Pode, who has presented the things very nicely. These 3 examples are there for this particular event as a first session. Those are inspiring the new generations. I'm very happy that the organizers and the conveners, organizers like Dr. Kokode and conveners like Dr. S.J. Doble sir, they have given this opportunity to chair first technical session, in which all the big guns were there. And I'm very sorry that my audio was not proper earlier. Now I could do those honor. I'm very much thankful to all these technical speakers for accepting the invitations and delivering the talk in due course of time. And organizers are being thankful. I'm thankful to organizers for giving me this opportunity to chair this session. Thank you. Thank you very much, sir. Now I hand over this thing to Ritesh for further proceedings.
Thank you very much, sir, for giving your valuable insights on ICRTM 2020. So I'm sure your valuable talks will help us a lot in understanding the concepts of recent trends in advanced materials. Once again, thank you so much for your words of wisdom. It will be great pleasure for us to listen you again in our future events. Thank you so much, sir. Now it's time to move towards our second technical session. Ladies and gentlemen, I know all of you are eager to sink into the depth of our second technical session, our eminent speakers of this international conference. So let's move towards our second technical session, in which we are going to have Professor Abdulara. Unfortunately, he could not deliver his talk. Professor Michels-Camarta from Delft University of Technology, Professor Douglas Nikita, Paris, France. And the chairman for this second technical session is Professor H.J. Doble, Department of Physics, RTM Nagpur University, Nagpur. So may I now request Dr. Atul Elpure to please anchor this second technical session. Please, Dr. Atul.
Thank you, Kode sir. Ladies and gentlemen, I know we all are eager to sink into the depth of our eminent speaker of this international conference. So let's move toward our second technical session. I, Dr. Atul Erpude from NS College Brahmapuri, feel extremely privileged to anchor this session. We are fortunate to have Professor H.J. Dobre, Department of Physics, RTM Nagpur University, Nagpur, as a chairperson for this technical session. On behalf of ICRTAM 2020, I welcome the chairperson of the session. May I now request Professor H.J. Dobre sir to introduce our eminent speakers and also to conduct this technical session. Please, sir.
Okay, thank you, Dr. Atul Erpure. I'm very happy to consider me as a chairman of this one of the session. In this technical session 2, for the 3 talk, one is the Professor Abdul Aruf, second is the Professor Nikalsha Martha, and third one is the Professor Douglas Nikita. But unfortunately, Professor Aruf, his health is not good, so he's not presenting for delivering his talk, but he's send a message for good luck for this conference. So in this session, only for the 2 talk, one is the Nikalsha Martha and second is the Professor Douglas Nikita. So first of all, I invite Professor Dr. Mikalsa Marsa. So I'm just introduced the Dr. Martha. Dr. Mikalsa Domaska Martha is Assistant Professor at Institute of Optoelectronics, Military University of Technology, Warsaw, Poland. She graduated in Physical Chemistry in University of Warsaw, completed her PhD at Military University of Technology. She took the post-PhD project in short internship of University of Tübingen, Germany, and she done her postdoc in corrosive science at TU Delft, Netherlands. She is an expert in the electrochemical synthesis of nanomaterials, especially in anodizations of aluminum and titanate, as well as the influence of the material state on its property. She worked in the material science field and focused especially on synthesis and characterization of nanomaterial of photovoltaic, biomedicals, and spectroscopy applications. She received 2 awards for her PhD thesis, MET Reactor Award of the Distinguished PhD thesis, and the Polish Prime Minister Award of the Best PhD thesis from all the dependent theses in the Poland last 2015 and 2016. She received a scholarship for an outstanding researcher from the Polish Ministry of Science and Higher Education for the entire academic work. She was principal investigator of the 6th project. Dr. Martha is co-author of more than 35 scientific publications, and her index, H-index, is the 40. She is the reviewer also so many good publication, and she is also a member of the very good publication. Lastly, Martha is my research collaborator, and she is very hard worker. And one of the good things, she is only one lady is the international speaker. So I congratulate, and she's a popular invited speaker for India. in the last month, she delivered 2 or 3 invited talks in the different part of the country. So, Dr. Martha, please come and start your presentation. Thank you, Martha, for your accepting our invitations. Thank you.
Hello, Sanjay. Hello, everyone. It is nice to see you. I'm very glad to be here, and I thank you for this invitation. I hope my talk will be interesting for you. I hope.
Please display your.
Okay. I try to share my screen. Could you tell me if you see it?
No. Just you share.
Okay.
No. Just you share.
This is okay?
No, ma'am.
Or not yet? You're showing.
Right. Yeah. Okay.
Yeah, this is okay? Great. So today I will talk you about anodic oxide, which are the very advanced materials. And few words. I'm now in Warsaw, in Poland, in the middle of my beautiful country. This is the capital, the Warsaw, and this is my city. It looks like this. You can see it. This is our symbol of my town of Warsaw, and this is some side of beautiful nature in Poland. So if you will have opportunity to come to Poland, I invite you. This is a very beautiful place in the world. And okay, today I will talk you a few words about oxide layer, nanostructured oxide layer, and anodic oxides and anodization. I will talk about how the setup for anodization should look like, and what we can change, why it is important to change the morphology or structure of these materials. Okay. So, the fabrication of nanostructured oxide layer can be done by electrochemical method. This is simply enforcement of current flow between cathode and anode. And during this process, on the surface of anode, the oxides are created. And this oxide have very different and amazing properties. It could be colored, it could be very nice arranged, and it could be used for nanofabrication or for some catalytic application. So everything depends what kind of metal of anode we used and what parameters of anodizing we choose. So here you have some example of anodized surface of aluminum and titanium anodized surface. And as you can see here, this is the rainbow color. So this is something what could be used, for example, in implant. Of structural color can be used for differential the size of implants, for example. And in the macroscopic view, the oxide could look like this. For example, it could be nanotubes, like in the case of titanium anodizing. It could be nanopores, like in the anodizing of aluminum. It could be also the sponge, or some porous layer without any arrangement. I will show you this later. And it could be also type of nanorods fabricated directly on the surface in the case of fabrication of anodizing of, for example, copper. So yes. And generally, anodizing is used for corrosion protection of metal. This is normal for aluminum or titanium. Very popular for this case. It's chromic acid anodizing, but this is this is danger also, because now the regulation of the European Union avoid to use this compound. So we try to find the new corrosion protection composition of electrolyte, because chromium-6 is carcinogenic. So yeah, we want to don't use this anymore. Okay, we can also give the attractive design of elements, for example, like in the Fisher here, Fisher elements, or we want to also add some color for implants to make different color for different size of implants. This is very important for VET, for example. In that way, we can also produce the semiconductors in the form of nanorods, as you can see here. This is template used for nanofabrication of copper, I think. We can also create a simple matrix for creation of nanomaterials. So we, for example, use anodic aluminum oxide for template to nanofabricate other metals, other nanorods. And in ideal case, our aluminum oxide matrix looks like this. So this is hexagonally arrangement nanopores straight to substrate. And here we have some main parameters. So diameter of pore, diameter of cells, anodic oxide thickness, and thickness of barrier layer. Because anodic oxide is end with this half cycle here. So yeah, this is also important how thick this barrier layer is. And how we prepare anodic oxide? Generally in very simple equipment. This looks schematically like this. So we have two electrodes, we mixed the electrolyte solution, we have cooling water to make sure that we have stable temperature during process. We apply the voltage, and this is everything. So equipment is very simply, relatively low cost for this method. And where is challenge? This is not obvious that we simply get something like this. This is very difficult to find good parameters to make good oxide layer simply. To help us, we can, for example, measure the current curves. This is the curves of current density in the function of time. And when we look at these curves, we have four etaps, 4 steps. And at the beginning, the oxide layer, the density oxide layer is created on the aluminum surface. After that, in this barrier type oxide, some cracks are formed, and then we observed the decrease of current density. When in some next step, the pore from this cracks in barrier layer start to migrate. So the current density starts to grow. And after that, our pore grow stably, and we also observe some stability of stabilization of our curves. Also, for each use normally electrolyte, we have some anodizing windows which describe the parameters of voltage, the range of voltage, which give us almost ideal arrangement of nanopores in the case of aluminum oxide. So, as you can see here, the most popular electrolyte is oxalic acid, sulfuric acid, and phosphoric acid. But also some other acids are studied to decrease the possible cell diameter for anodic oxide and for simply get new properties. So this is only some example, because also some mixed of electrolyte can be used, but it's also demanding a lot of study to find this window, because this is defined only for specific condition, for specific concentration, specific temperature, specific pH of electrolyte. So yeah, this is a lot of work, simply. And in reality, our anodic oxide could look not so beautiful. For example, like here you can see this is some branched nanopore, some mesh. Here we have the structure which is more like sponge, not like nanopore. But this everything depends on the condition which we apply during fabrication. So why is it important? And if it is important, how does anodic oxide look like? Yes, this is important for some specific application, for example, for nanofabrication, because this is the key factor. We have to have very beautiful anodic oxide layer on the top of aluminum if we want to use this for nanofabrication. Because when we fabricate some nanorods on some semiconductor, we want to have this nanostructure in good arrangement. But for example, when we use anodizing for corrosion protection, this is totally not important how this oxide looks like. Here it's important only the thickness of barrier layer and also the thickness of anodic oxide. And the nanopore could be branched, could look very bad, and this has no influence on the properties in the corrosion protection. But if we want to use anodic aluminum oxide for nanofabrication, we have to prepare very carefully now our matrix, because this is very important. And what could influence on the morphology of anodic aluminum oxide? Mainly everything, actually, because when we change operation condition, like current, voltage, time of the process and electrolytes temperature, or even type of anodizing materials. It could be, for example, very pure aluminum substrate, which is very expensive also, but we also could use, for example, aluminum with industrial purity, which is much cheaper, and it is possible also to get good matrix on this type of aluminum. We can also change experimental setups like rotation speed or inter-electrode separation. This is also factor which influence our resulted arrangement of nanopore. This is totally negligible by most of researchers, this parameter, but this is also influence on our regularity ratio or other things. Also, we can change the properties of electrolyte, pH, viscosity, composition. We can also add some additional elements, because in that way we also can influence on our matrix. And why this is important? Because this is material science. And when we change the properties of we want to change the properties of materials by changing the structure and the morphology of it. So what we can do in the case of aluminum oxide? Okay, we can change composition of electrolyte. Why? We want to some anions into the anodic aluminum oxide, into the structure of it. And we can do it in one process during fabrication, simply. Because when the aluminum oxide grow, the negatively charged anions are being incorporated in our oxide layer during the process of growth of this nanopore. So we also find that if we have higher anodizing voltage, the greater oxide growth rate is observed, and also more ions are incorporated during our process into anodic aluminum oxide. And in this way, we can prepare, for example, aluminum oxide with luminescence properties. As you can see here, we incorporate here some chromium inside aluminum oxide, and with higher voltage and higher temperature, we observe more chromium anions inside our matrix. We also find that this method could be applied for production of luminescence materials formed by electrochemical method. We do similar research with copper anion, and we also receive some good results because we also incorporate copper ions inside our matrix. What is interesting, the matrix, anodic matrix, anodizing in chromic acid looks like this. This is not very well, not good arrangement of nanopores, but when we do similar research with copper anions, we receive very beautiful, as you can see here on these pictures, a very beautiful arrangement of nanopore. Not hexagonal, but still very beautiful. And we proved in this research that the greater oxide grow rates, greater voltage and greater temperature influence on the copper incorporating the walls of anodic oxide layer. And we confirm that this is possible to get photoluminescence from this materials. We try also do similar research with big, relatively big particles, indigo, organic compounds, indigo carbide. Okay, sorry, I forget. And it was proved by Raman spectroscopy that this indigo carbide was incorporated in our oxide. So it was made for the first time, and this is really fantastic because we can try this with other elements, and this is possible to incorporate even big organic particles inside the anodic oxide layer. So this opens some doors for a lot of good research. And here I want to show you what I can do with anodic titanium oxide. Here the materials of anode was titanium, and this is very interesting materials because anodic titanium oxide generally consists of nanotubes, and this is used for photocatalytic reaction for production of hydrogen from water, for water splitting, for example. And generally this is produced in organic solution electrolyte, for example, based on glycol or glycerin. And I want to do something different. In my other research, I find that viscosity of electrolyte influence significantly influence morphology and type of oxide. So here I decrease the viscosity of electrolyte, and I use ethanol-based electrolyte. And in this case, I obtained some very interesting morphology of anodic titanium oxide, and the parameters of this, properties of this morphology could be placed between anodic titanium oxide made in water-based and organic-based electrolyte. So this is something between. And what's more, I obtained very interesting properties, optical properties of these materials, but I can't show you this yet because this is during publication. But this is some way to change the properties of materials by changing the fabrication method. And yeah, maybe next time I will show you more. And okay. Also, some negligible parameters like inter-electron separation. I find that this have significant influence on arrangement of nanopore. When we prepare anodic aluminum oxide in the solution of water-based solution of oxalic acid, the change of anode and cathode distance influence very in big step, influence the arrangement of nanopores. So if we prepare anodic aluminum matrix for nanofabrication, this separation of electrode is K factor. And of course, this is maybe only arrangement of nanopore, but when we do when similar research was done on in more viscous electrolyte here, this is not my work, but I like this work. It was the effect of interelectrode separation in the case of aluminum was studied, and when the change of distance between titanium and platinum was studied, it was found that with this interseparation distance, we change in big very much. We change very much the thickness of anodic oxide layer. So here, as you can see, this may be some 3 microns, and here, when the electrode was very close one to another, the thickness was 10,000 or 20,000 more than this first time. So this is a very important factor. Okay, and when we change the anodizing substrate, we also receive other matrix. And generally, for nanofabrication, as I told you before, the high purity aluminum are used, but this is very expensive materials in the form of tin foil. This is very expensive. So I found that maybe this is possible to get some good operation condition for preparing of anodic aluminum oxide on the other aluminum substrate. So I chose industry purity aluminum AA1050. The only 5 minutes? Really? Oh my God. Okay. So yeah, so I received some good results, and in the specific condition, as you can see here, this is regularization of nanopores, and this is our technical pure aluminum, and here is very pure aluminum. The difference in regularity was negligible, but the difference in price of substrate was, oh my God, very high. So also this is maybe less important. Okay, and other things. When we want to incorporate too much other anions inside aluminum oxide, we can also damage our matrix. And for example, here, this is anodic aluminum oxide, but we incorporate a lot of sulfate anions here, and our matrix start to form some halos, some cracks, and something like this. Simply, if we apply too much other anions, we damage our surface. Maybe this is important only in some specific application, but still. And other things, anodic copper oxide. As you can see here, with increasing voltage, we receive other morphology of nanorods, crystalline nanorods of copper, which are produced in one step, anodizing, and we don't have linear relationship between nanostructure diameter and the applied voltage, but still we have some increasing of diameter of nanorods. And what is important, when we have greater voltage, the more CO2O, the phase, the more this phase is obtained in our nanorods. And this type of materials can be used in photocatalysis to produce, for example, hydrogen, and we want to make more research on it. And project, so don't be afraid and try. Simply You have to write apply, and then you create your own change to have your own research, yeah, on your research way. So this is my project. I want to develop some new substrate for surface-enhanced Raman spectroscopy based on anodic titanium nanofibers. As I told you before, generally anodic titanium oxide grows in nanotubes form, but I also received something like this. This is nanofibers. And I want to use this substrate for cells. Why? Because in cells, the morphology of substrate is important because of this reason. So we want to have a low background, we want to have repeatability and uniformity surface of substrate. We want to have long-term durability. And why we can use anodic oxide for this specific purpose? Because this is stable in time, this type of materials, and the regularity of nanostructure made in this oxide are good or very good. And
Martha is 2 minutes.
Okay, and for example, in the case of anodic titanium oxide, we can also use these materials after annealing to create some self-cleaning substrate, for example, because anodic titanium oxide have photocatalytic properties. So we can remove the residual particle on cells after cells from the substrate. Okay, and this is how this is used in this moment. Okay, and I describe this in my news chapter. So if you want, come and read. Open access, and this is also some new idea to create oxide layer on intermetallic phase iron aluminium. And this is some example how this layer could look like. And okay, I think my time is end. So so thank you for your attention.
Thank you, Martha. You are already so good discussion of the anode oxide materials synthesis by electrochemical method, and it's some of the applications also. And these are applications nowadays very much more important in the some of the different part. It is also some of the antibacterial activity side also. So you are doing very good on the titanium oxide, aluminum oxide, copper oxide, and tin oxide also. So now, thank you very much. And you are one of the lady in my international speakers. So I'm special thanks to you. So I'll also invite in the coming again next conference. So thanks, and you continue our collaborations. Thank you,
Okay.
Okay.
Thank you too.
Thank you. So next speaker of this technical session, Professor Douglas R. Nikita. Professor Douglas is try to explain his topic on the characterization of the graphene sheet by microscopy technique. Professor Douglas from the Microscopy Center of the UFMD, Paris, Scala University, France. Sir did his MSc in 2001 and DSc in 2000, MSc in 2001 and DSc in 2003. Professor Douglas working on the advanced functional materials, especially the 2D materials, and I'm very happy the CV is very strong, sir. It is not possible very few times I will explain your CV. You have published those very good publication and very high impact factor especially, and his citation is also very much more. So you are our coming collaborator. So I welcome you in India, and you continue this type of collaboration in future also. You are the special invited by the Vishal Panse. So I'm very happy with my students. Vishal Panse is very strengthened the collaboration with you. So I just invite to you deliver your talk, and thank you very much for your invite coming here and for the invited speaker. Thank you, sir. You can start your work.
Okay, thank you for the invitation. Everyone can hear me?
Yeah.
Okay, thank you. So first of all, I would like to say thank you to organizing committee for the invitation, for the efforts to promote this event, and for the opportunity to share with you a little bit of my work. Okay, let me try to.
Yes, you share this your screen on the top.
Yes, I'm trying to do that. Okay, can you see my screen?
Yes, sir. Yes, yes.
No.
Good.
Well, and my name is Douglas Nikita. I'm a researcher on a microscope center of Federal University of Minas Gerais in Brazil. And I'm spending a sabbatic time at Laboratoire de Physique du Solide at Université Paris-Sud, Paris-Saclay in France. Yes. As just I talked to you, I come from Brazil in a state called Minas Gerais and the southwest part of Brazil. I live in Belo Horizonte, is the capital city of the state, where we have Federal University of Minas Gerais. Belo Horizonte, it's a very nice city to live, to work. It's a very green city. Nice hair, nice food. It's not so hot, it's not so cold. So it's a very beautiful place to visit. Please come to visit us after the crisis of Corona passed through. Well, in this university, we have the Microscope Center of Minas Gerais. It's this laboratory is recently was conceived as an interdisciplinary and multi-user center for research and technology-based activities with infrastructure focus in electron microscopy, scanning probe, and microscopy by ions, and all sample preparation devices necessary to develop these techniques. It's not exclusive for the university or students. This laboratory is open for everyone that's work in research and development of the science material. We have users from all Latin America and few users from the USA and Europe using our facilities. Well, among our facilities, we have 2 scanning probe microscopes, ultra high vacuum system for scanning tunnel microscopy, 4 scanning electron microscopy. These 3 are field emission guns, an electronic probe analyzer dedicated to wavelength dispersion spectroscopy, 2 thermionic transmission electron microscopes, and 1 system. There is another one to start to work in soon, fluorescence systems. All these machines are working as fully as their models allow. Well, marketing apart, let's talk about science. Well, since the seminal paper of Novoselov and Andergain, an explosion of results has occurred, showing all fantastic properties and applications of graphene in 2D materials, as well as a multitude of the other 2D materials also have been isolated and grow by a variety of different methods, including the original mechanical exfoliation shown in this paper, and followed by chemical vapor deposition, and more recently, liquid phase exfoliation called the LPE. LPE is a promising candidate for high throughput and low cost production of graphene and other 2D material layers. Since these all applications of graphene appear, more and more people are thinking in how to produce huge and high quality graphene material or low layered materials. So the LPE is very appropriate for this goals, because LPA uses the shear force in a mixture of 2D layered source and in a specific dispersion liquid using some kind of surfactants. Here only a schematic to show the problem. This setup that I'm showing here don't work. I tried, believe me, don't work very well. And if the shear force with the specific surfactants to promote the separated of the layered flakes, or using LPA for if this setup runs for enough time, few layered solution with a very monolayer concentration is obtained. Okay. Even though large non-exfoliated graphite flakes may remain in dispersion, they can be centrifuged and separated from the graphene flakes. So at the end, we will have a very rich graphene dispersion. Well, it's worth to mention again, we are talking about needed to large-scale production, and large-scale production require robust and truthful characterization process. And although LPA is a powerful technique for this goal, it's a powerful technique for graphene production, there is still no standard procedure for a reliable size quantification and classification of this technique, of these materials. In morphological characterization of 2D materials, there are at least two important parameters to be measured: the lateral size and how many layers form the flake. We have monolayer, 2-layer, 3 layers, thick layers. So it's interesting to know these two parameters to make a morphological characterization of the result, the final results. So different techniques like atomic force microscopy, scanning electron microscopy, transmission electron microscopy are employed to characterize these parameters. But sometimes, and most of times, the results from these different techniques have no agreement, or in some cases they are completely different. Well, from these three techniques, the lateral size that is defined average of the Ferrier diameters in the simple equation come here. And the number of layers can be measured also by atomic force microscopy. It's calculated by the flake height, which is measured directly from the image. We can count directly the number of layers from the high resolution TM images, or we can extract indirectly from the intensity of the G-band in Raman, the intensity of the G-band in Raman spectroscopy. There are a lot of articles talking about this Raman spectroscopy in graphene to extract the number of layers. So, initial attempts to standardize such quantification have been carried out, but some deeper aspects of the statistical interpretation of these results are still missing. So we try to show you something that looks like obvious, but from the surprise of the people that work with me in this project, it's not so obvious. Well, many efforts, besides the extremely high lateral resolution reached in a TEM image, we do not have any quantitative information from the thickness of the flake we have in the image. And this is somewhat frustrating because in this kind of material, we almost feel the thickness of the sample in the image. As example, in this case, we can see the folded part, the thin part, the thick parts. So we have a very high lateral resolution in this image, but we cannot take information of the thickness. So think in this line, many groups developed some procedures to extract this quantitative information about the thickness sample from the TM images. This group is work by Stefano Rubin and collaborators. They show a linear relationship among the intensity in the TM image and the thickness of the sample. So the procedures consist in take intense image in a special condition that we call tubing condition. So we take the intensity of the image in a region in vacuum. So this is zero intensity. So we take a measurement of the number of the layers in a folded part, as in the last slide I show you. From this measurement, we apply this equation to extract this factor of absorption factor. With this number, we can go back to image and pixel by pixel, we can change the values from intensity to thickness, transforming this image in an image with information about the thickness of the sample. It's looked like a dream for people that work in microscopy, mainly in microscopy and transmission electron microscopy. But it's a very time consuming because we need to take this flake by flake. And there is a bias for operators. Small flakes will be not considered by people. Another approach developed within TEM is from the diffraction factor. Hernandez, using a method developed by Meyer, here the references, show a systematic way to identification of graphene by analysis from electron diffraction patterns. Here we have a graphene flake folded onto herself. We have here a monolayer part and bilayer part. So these people show that in monolayer part, the first order diffraction spots are more intense from the second order. And the thicker parts is opposite. The second order spots of diffraction pattern are more intense than the first order. So using this method, people take flake by flake, a lot of diffraction patterns, and they can make a distribution of the number of layers in function of the number of flakes that you have. So it's possible to know how your dispersion is in terms of number of layers and correlate this in lateral size in a very high resolution image. Again, it's a process that spent a lot of time because it's necessary to take flake by flake. And to put these small flakes in correct condition and diffraction condition, it's not so easy. Again, we have a problem of bias of the operator here. But work very well, is truthful inside of this small volume. Okay. So as I try to show you the characterization of liquid phase exfoliation samples by TM has some drawbacks. Normally it uses a holy carbon grid where measurable flakes must be partially suspended in the hole on the grid. This procedure might introduce a bias in the measurement, since the small flakes, it's another drawback. These small flakes might not adhere, has no good adherence to the grid, and therefore may not be properly accounted in these statistics. And as I told you, these methods discussed above can be destructive, not in the case of TM, but when talking about scanning electron microscopy, does not suffer from the same problem of TM, since many flakes can measure it simultaneously. However, due to the low atomic number of carbon and the deep, even a low acceleration energy in SEM, the signal that comes from the substrate is order of magnitudes bigger than the signal from these atomic layers of carbon. And this hinders the identification of few layered flakes and produce a low contrast image, making, here we have an example, making difficult to measure the borders of the flake and making necessary to set the conditions of measuring to optimize the image. We need to set the conditions of operation flake by flake and putting the SEM also as a time-consuming methods to characterize these morphological parameters of the graphene flakes or 2D materials. So again, we are talking about cheap and large-scale production methods. So we need to fast and robust characterization methods. In this context, atomic force microscope appears as an interesting alternative. Besides the slight lower lateral resolution than TM or scanning electron microscope, atomic force microscope still have good resolution for this kind of material. Well, in a FEM experiment, a cantilever with a very thin tip interacts with the sample. When the interaction between the tip and the surface of the sample change, the signal in the photodetector also change. And from this, we can take an image that represents this kind of interaction, which can be electrical, magnetical, or morphological. So from these results, from this image, like this one, from atomic force microscopy, we can extract simultaneously results from the height of the sample and the lateral size of the structures. So from these results, we can take a powerful space phase like this one, when we can correlate the number of layers and the lateral size for a huge numbers of structures in just one image. In this example, we have a very rich distribution in more than 2,000 flakes. So using this kind of measurement, it's possible to quantify the lateral size, number of layers, and due the 3D characteristic of the material and the measurement, we have take area and volume of thousands of structures and directly correlate the lateral size and the number of layers, like in this case. And at first analysis, we see that in these results, for example, we see that most of flakes has less than 10 layers, and they are until 200 nanometers of lateral size. From this kind of analysis, it's possible to set the initial parameters of production to optimize the process of production. More than this, behind of these results, there is a point which we need to few people pay attention, but we start to pay attention in this. These flakes here, in this region, we have here few big and thick flakes. They are few flakes, but they are few and thick. So if we think just in numbers, okay, most of my material is graphene. But if you think in volume or mass, most of the mass of my sample is concentrated here. And this is not good because this deal with the purity of the final solution. It has a great impact on actual mass than 2D materials. So the popular interpretation of the number of layers and lateral size may lead a misleading analysis of the actual purity of the sample. Well, to show this point, we proceed a follow experiment. From the same LPA graphene solution, we prepared 2 samples for atomic force microscopy analysis. This first one here is as produced. We a part of the solution in a silicon substrate, oxysilicon substrate, and take the result. So we take another part of the same solution and they pass through a very drastic process of centrifuge.
Hello?
Hello? To extract the bigger.
So continue, sir. Continue.
इधर का क्या देखा है इस पर डिपेंड करता है ना. कैंप देखा है, दिल्ली यूनिवर्सिटी का नॉर्थ कैंपस देखा है.
अरे सर continue.
Okay.
This is
okay.
the unnecessary time. Okay, continue, sir.
दिल्ली यूनिवर्सिटी देखी है. हाँ, दिल्ली यूनिवर्सिटी से आगे आओगी.
Okay, 1 minute.
विजयनगर आता है.
1 minute, sir. 1 minute.
Okay, no problem. This happened.
Sir, you continue. Don't worry.
शक्ति नगर चौक से सीधे आ जाए जीटी करनाल रोड पर. वहां से किसी को भी पूछे कि कल्याण विहार में डीडीए फ्लैट्स कहाँ पर हैं.
Sir, please you continue. This is some sound from other end.
Okay, I'm trying.
Colony.
This is the talking next chairman with any other one. Please you continue.
Okay. So from this material, after the centrifuge process, we extract this bigger structures. And we can see clearly are 2 different samples now. We have 2 different samples now. But if you look for the statistics, here I change a little bit the way to present the graph. We consider an material with less than 10 layers as graphene and more than 10 layers like graphite. Okay. From the height measurement in the IFM experiments, we extract the number of the layers. So, and H0 is the height of the first layer. And so, after this procedure in this spacer phase, we see from this picture, the samples is clear. This bigger and thicker and flakes that we see here are not present here. But when we look at the numbers, the nude numbers, the sample are the same. Look at this. lateral size and the number of layers for the non-centrifuge sample is the same for the centrifuge. Again, if you look only for these numbers, we are in a misleading interpretation. It's necessary to look more deeper in these results. And atomic force microscope allows us to look in deeper. We can look for the volume and the mass of this material. So what we do? We wrote, because our informations about diameters, area, thickness are present in these final results from atomic force microscopy. So we wrote a routine to go back in these results and make a classification in number of layers in the image. For example, in blue, we have flakes that has from 1 to 5 layers. And in red, the flakes that have 6 to 10 layers and more than 10 layers. We call, we paint in green and white for the bigger ones. So from this kind of image, we can extract a more precise classification of the material. So now, again, if I look only for numbers, look that for 2 samples, here and here, the amount of graphene is equal. But now, if I look for volume, we have a more truthful results. This sample, B, centrifuge sample, has more graphene than graphite. And now, when you look at the volume from this separation method here, we have a more truthful results here. So the numbers now make more sense, but it's necessary to look at the volume of the sample. And as I just talked to you at the beginning of my presentation, this looked like obvious. But for my surprise, when we make a revision on literature, and in the last years, a lot of papers as discussing and how to make a good characterization of 2D materials, and nobody's pay attention on this. So we spend the time in making these results. We are very happy with the results that we found here. So, and to finish this, my short presentation, and liquid phase exfoliation is a permission method for large-scale fabrication to feed the needs of the whole industry of 2D materials. Large-scale production methods need fast, robust, and reliable characterization methods for quality evaluation of the material. In this context, despite atomic resolution, electron microscopy has set their drawbacks that make it inappropriate for massive characterization of the materials. It is necessary to make interpretation a little bit deeper of the results from the atomic force microscope to understand better the purity of the sample. And on this basis, 2D, 3D mass content should be the standard parameter in the characterization of inducer for 2D products, not only number of layers or size, but the 3D characteristic of the feature of the material needs to be considered. Well, I think I talk very fast. So for who is interested in more details, we have these 2 articles from the group where I was working in Brazil that explain in more details what I try to show to you. For now, and I would like to say, please feel free to write me, to contact me if you I can help you or something. And for now, thank you so much for your attention. Thank you so much again for this invitation. And I'm very glad to this opportunity to share with you a little bit of my work.
Thank you, sir. Thank you very much. And there is, here you are presenting the very good work, and your papers also very high level. So our participants are very much happy for your good presentation on the different parts of this graphene. And this work is very interesting in the future applications. So I'm very thankful to you. And now this time the session 2 is over. I'm very thankful to the both of speakers, Dr. Martha and Dr. Douglas. So we are giving the time and presenting very nice work of this conference. I'm also thankful to the organizer for give the chance for me chairmanship. And thank you very much. Atul Erpude, please over the Atul Erpude. Atul. Atul Erpude. Ritesh. Ritesh will continue. Ritesh will continue.
Yes, on behalf of Dr. Erkude, I thank first of all the chairman of this conference, Professor Ajay Doble, and the speakers, Professor Mishalka Marta and Professor Douglas Mikita, for delivering their really knowledgeable speech. Am I audible?
Yeah, yeah.
Once again, thank you so much, sir, for your words of wisdom. It will be a great pleasure for us to listen you in again in near future. Thank you so much.
Thank you. I'm enjoying this chairmanship. Thank you very much.
It's our pleasure, sir.
Okay.
Now it's time to a lunch break. The delicious lunch is waiting for you. So
Well,
we'll resume here.
sir, this is the e-lunch. E-lunch.
Yeah, it's a e-lunch.
But this is the lunch due on the organizer.
Yeah.
Yeah.
Whenever this corona pandemic will be over, we will definitely
Okay. Thank you. You are with us.
Yeah, so
Thank you,
dear
Martha, and thank you, Douglas Professor. Thank you.
Dear participants, we will resume here by 2:20 p.m. Indian Standard Time, and after this, Dr. Vishal Panche will host this technical session 3. Thank you all of you.
Thank you, Douglas sir.
Okay, thank you. Bye-bye.
Bye.
Bye-bye.
Bye.
Hello. Hello.
Hello. We will resume by 2:20 p.m.
Hello.
According to Indian Standard Time here. So till then, have a nice time ahead.
Hello.
Hello.
चालू करो. मी का
Hello. Actually, we are running quite late. It's all 2:20. So within, let me ask the organizers.
Ladies and gentlemen, we rarely get this kind of opportunity to listen to the words of wisdom. May I now request Honorable Dr. Nilesh Gawande sir, Chairman Nehru Yuva Krida and Sanskritik Mandal, Chikli District, Buldana, to address the gathering. Please, sir. Gawande sir.
स्पीकर काढायला
तिथे ऑप्शन येते फोन आला ना गेले नाही तर स्वस्त असाल सेफ असाल सर्व असा या देशामध्ये प्रसाराच्या पार्श्वभूमीवर पूर्ण जग
Ayala. No sound. Hello. Third technical session will start at 2:20 to 2:10, not 20, 2:10. And in this third session, chairman is Professor P.D. Sare, Department of Physics, Delhi University, and 3 talks are there. And last session is 4. After that, and chairman is the Arun Banpurkar, sir, and again 2 talk. So now, just waiting for up to the 2:10. After that, just sharply start in the third session at 2:10 after this lunch break. So please wait for the 2:10. So do you don't move anywhere and just you start at the 2:10. Thank you. I will catch the first photographs. Thank you.
Okay, dear participants, we'll have a short break and we will resume by 2:15 for a third technical session as Professor Doble has already. Uh, hello, I'm audible.
10. 2:10.
2:10, sorry, extremely
Yeah.
sorry, to 10 p.m. according to Indian Standard Time. So we will resume by 2:10 for third technical session. Thank you. In this session, we will have 3 talks. Professor Mamadou Diallo, CAMS Research Institute Africa, and then Professor Thomas Justil, FH Munster University, Germany, and Professor Florian Bohr, FH Munster University. So the chairman for this third technical session will be Professor P.D. Sare, Department of Physics, Delhi University. And after that, we will have fourth technical session and validity function. So let's resume back by 2:10. Thank you.
चलो भारी
आवाज नाही तर याचाच कमी करून पास
ऐकू द्या फॉरेन बोलणे असे बी राहते.
हॅलो
हॅलो रितेश डायलॉग सर झाले का जॉईन? हॅलो हॅलो
हा
डायलॉग सर झाले का म्हटलं?
फोनचा आवाज येतो. एक सेकंड दिसत नाही, चेक करतो. नाही दिसत आहे. प्रोफेसर नाही रे. Professor P.D. Sahare sir has joined. I welcome for this technical session 3.
किती वेळ आहे अजून?
हाँ हेलो सहारे सर हाँ सहारे सर हेलो सहारे सर
Yes.
there are speakers they are joining within a few minutes then
Okay.
then we will be able to start the session.
It's okay. All right. Just give me a ring.
Yes.
Just give me a ring when they join or when you have to start.
Yes. Okay.
Okay.
Sare sir. Sare sir. Hello
Yes,
Sare.
yes, yes. I'm around.
आपका शर्ट बहुत स्मार्ट है आज।
Thank you.
और आपका स्टेटस फोटो कहाँ का है? छोटे छोटे बच्चे स्कूल में गए थे क्या?
पता नहीं।
छोटे छोटे बच्चों के साथ में आपका स्टेटस फोटो है।
हो सकता है किसी स्कूल में मैं
हाँ, so I thought visited some school and there you delivered the lecture. Therefore, that is a nice status picture. We ring this guest on the WhatsApp, and they said they will be ready by 2-3 minutes.
let them join. That's what I'm saying. Let them join. I'm around, and then we can start.
उनके 5-5 मिनट कम करना पड़ेगा।
हाँ ठीक है, देखते हैं कितना टाइम दिया है।
हाफ एन आवर दिया है।
हाँ?
हाफ एन आवर 30 मिनट्स।
ठीक ठीक ठीक, बट लेट देम जॉइन नो फर्स्ट। कौन कौन है वो? तीन नाम भेजे हैं, तीनों है नहीं?
एक मिसिंग है उसमें से।
कौन? नाम बताओ।
कौन है आज 3 में से कौन मिसिंग है? तीनों प्रेजेंट है।
Thomas Justin missing.
Oh, Thomas Justin will not be delivering.
Thomas Justin will not be delivering.
Okay, all right.
It is Dilo and Boss.
Okay.
Only two.
So they have made my job easy. He has made my job easier.
Yes, yes. And time will be automatically now compensated.
Okay, all right. Let me know when they join.
Yes, yes, yes. We are in touch. We are in touch.
आज आप बहुत स्मार्ट लग रहे हैं कोकोडे सर।
बोल हा बार जॉईन झालेले आहे. आपण सुरू करून घेऊ. बार तिसऱ्या नंबरचे गेस्ट. बार तेच ते सुरू करून घेऊ. अतुल स्टार्ट.
Let's start, sir.
Ladies and gentlemen, I know we are.
Sahare sir, please.
Yes.
Sahare.
Ladies and gentlemen, I know we all are eager to sing into the depth our eminent speaker of this international conference. So let's move toward our third technical session. I, Dr. Atul Erkude from NH College Brahmapuri, feel extremely privileged to anchor this session. We are fortunate to have Professor P.D. Sahare sir from Department of Physics, Delhi University, Delhi, as a chairperson for this technical session. He is the prominent alumni of NH College Brahmapuri and also the prominent alumni of RTM Nagpur University, Nagpur. On behalf of ICR TAM, I welcome the chairperson of this session. May I now request Professor P.D. Sahare sir to introduce our eminent speaker and also to conduct this technical session 3. Please, sir.
Over to
Okay, thank you very much. At the outset, I would like to thank the organizers, especially Dr. S.J. Dhoble and Dr. Kokode for giving me opportunity to chair this session. In this session, I think we have two speakers. So the first speaker of the session is Dr. Florian Bauer. He's a young professor at the Department of Chemical Engineering, FH Münster University. And I think he doesn't need much introduction. After going through his CV, I found he's a man of luminescence and developed a lot of phosphors. He has so many papers to his credit. So I invite Dr. Florian Bauer to present his talk in this afternoon session. Thank you.
Okay, yeah, thank you for a kind introduction. So I will try and share the screen. So, okay, so
व्हिडिओ तो यांचा व्हिडिओ ऑन करा.
okay, so I hope everyone can see the screen.
Yeah, it is visible.
You are audible too.
Yeah, you are audible and your presentation is also visible.
Okay, so yeah, let's begin, or I switch back to the first slide. So the topic will be warm white LEDs with using europium-3+ on the basis of uranule, so uranium. Okay, so first, short introduction of the research group I'm part of. So as I already mentioned via email, so Professor Istel originally also wanted to hold a presentation, but unfortunately, some minor health issues, so nothing serious, but it prevented him, unfortunately, from attending. Generally, so we are working basically with everything in connection with luminescence, so luminescent pigments, physics, also nanoscale pigments, core-shell particles, especially some of my co-workers were working on that. And then generally optical spectroscopy and solid-state synthesis. Okay, so as a general introduction to red emitting phosphors, why are they important? So there are some nice photos or pictures here to show the difference between warm white and cool white. So I am aware that, or it came to my attention that in many countries actually cool white light is preferred, even in living conditions. So it's different in Europe. So I suppose it's maybe for cold countries, people prefer this warm white light. So you have to think about it that it's more important for Europe and maybe Northern America. So anyway, there's a quite pronounced difference. So this picture down here would show how does the LED look like if you have warm white light, so with a red emitting phosphor, and on the other side, so this right picture of a bedroom like up here, what happens if you don't have a red emitting phosphor. So generally, if you want warm white light, why would you even have an LED that is just emitting cool white light? So the maybe well-known reason is that it's the easiest way to fabricate an LED by just using a blue-emitting LED chip, so based on aluminium gallium nitride coated with some garnet doped with cerium. So then you end up with cool white light. So the big advantage here is that it has high luminous efficacy. Also, it's relatively cheap phosphor, like cerium. But the downside is that coloring rendering index is not as high because you're lacking the red light. And also, if you really want warm white light, then it's not really a suitable replacement for incandescent lamps that are known for emitting warm white light. So what can be done about that? You can add a red emitting phosphor, and this is what is done for quite a lot of time now. So it will definitely result in decreased luminous efficacy. So the reason for that is that in the red spectral region, the human eye is not as sensitive. So all the photons that go in the red spectral region instead of yellow or green, you will perceive less bright. So the lamp will appear less bright to a human eye. But of course, it also has advantages, otherwise it wouldn't be done. So big advantage is that the color rendering index will be better. So by the way, color rendering index means how faithfully can the lamp reproduce a color. So for example, if you have a red material, like this thing here, for example, and your lamp doesn't emit this color, then of course you also cannot see this color on the surface. So you need all the different colors in the lamp to be able to reproduce a color. So when adding a red emitting phosphor, then these LEDs can more or less 100%, not really, but close to 100% copy an incandescent lamp or imitate it. Okay, so Why is there still need to do some scientific investigation into this topic if we already have warm white light emitting LEDs? Well, the reason can sort of be explained with the help of this graph. So as I said before, red light, generally human eye has lower sensitivity. So no matter what type of red light, you will always have a slightly lower luminous efficacy of the lamp. But you can quite strongly influence how much less efficient it is by choosing the proper red wavelengths. So this is what this orange line is showing here. So you have on the x-axis the peak emission wavelengths of the red emitting phosphor. And then if you shift it from sort of orange at 600 to really deep red at 700 nanometers, you will find an optimal range where the color rendering index is really high. But the luminous efficacy has not yet started to decrease strongly. So this is sort of the efficiency of the lamp. So how brightly will the human eye perceive this lamp if you use a red phosphor with this emission wavelengths. So if you go too far to the red, so for example, manganese 4+ and oxides is emitting around 650, then you can see that the efficiency or efficacy of the lamp is already decreasing. And at the same time, the color rendering index is also decreasing slightly. So phosphor that is emitting around 620, 630 would be the optimum. So the currently used europium 2+ red emitting phosphors do emit in this range, but they have a really broad emission band. So they are emitting with peak emission in this region, 620, but they are also emitting down to maybe 580 and more specific, more important, even in the deep red spectral region because they have such broad emission band. So you lose a lot of photons because they are emitted in the deep red spectral region. So what you actually would want is a so-called narrow band red emitter that is having a peak emission around 625. So one example is manganese 4+ and fluorides. So that is also sometimes used, but fluoride hosts are a bit hard to synthesize and quite expensive. Also, it's patented by GE. So it's not like anyone can just use this phosphor. So there are some problems still. So another way, instead of using manganese 4+ and fluorides, you can use europium 3+. So with some aspects, it's quite ideal red emitter because it's emitting at 620, so close to this optimal range I was just mentioning. Thermal quenching temperature is usually quite high, so that means even if you have a high power LED that is can have temperatures higher than 100 degrees Celsius, maybe even sometimes getting close to 120, 130, the phosphor will still be emitting efficiently. Europium 3+ usually has a high quantum efficiency. You mostly don't have problem with concentration quenching. So that means you can put a lot of europium 3+ in a phosphor and it will still have high quantum efficiency. And in comparison to manganese 4+, the big advantage is that you don't need a fluoride host. So you can just use an oxide. So the spectrum here is just an example of how europium 3+ can look like. So since it's an FF transition, the emission will not change strongly. So it will more or less always look somewhat like that. So you will find some phosphors where europium 3+ deep red emission is quite strong. For example, in lutetium aluminium garnet, this emission is quite strong, which you don't want to have. But mostly this is a main emission from europium 3+. So exactly at the position where you would want to have it. So what is the problem here? Why isn't everyone using europium 3+ as red emitting phosphor in LEDs? Probably, or maybe some already know the answer. So the problem here is that it's only having FF transitions in the visible range, and these are quite strongly quantum mechanically forbidden. So the absorption is low because the transition probability is low. So this wasn't a problem for the fluorescent lamps because they are exciting with UVC light, and there you can efficiently excite europium 3+. But today with LEDs emitting in the blue spectral region, that is becoming a problem. So what can be done? Yeah, we were actually investigating this issue for quite a while now and have tried different attempts to solve this problem. So one of the newer ones is this core shell attempt, where we try and sensitize europium-3+ with cerium and terbium. The general problem there is, if you have cerium-3+ in contact with europium-3+, they will do so-called metal-to-metal charge transfer, and that will quench the luminescence. So in this attempt, we were trying to separate cerium and europium with this core shell structure. It also is actually working, but of course it's a bit complicated to synthesize because you need this core shell structure. So other attempts included using molybdenum-6+, so this is not really new, admittedly. It was already, I think, tried in several decades ago by George Blasse and co-workers. The problem there is mostly that quantum efficiency is low. Then we were trying to use terbium, but terbium also has relatively low absorption. And then recently we tried to use uranium, or more specifically the uranyl cation. So this is also not a completely new invention. So this is already known that uranium or uranyl can excite europium-3+, but it hasn't been tried recently to create an LED phosphor. So we were putting some work into that. Yeah, first of all, maybe some background information on the uranyl cation. So what is it? Yeah, it's showing relatively strong emission in the green spectral region in combination with quite strong absorption in the blue to UV, even down to UVC spectral region. So the reason for this is the absorption transition is quantum mechanically allowed. So that's, yeah, means it's high probability for this transition. So it's spin allowed singlet-singlet transition. And the emission on the other hand is triplet singlet transition that is spin forbidden. But for emission, that's not a problem, because once you have excited the uranyl, it has to emit somehow. So all that this forbidden emission transition does is that the decay time is relatively long, in the millisecond range. So since it's a complicated molecule, the energy level scheme is somewhat complicated, so I won't go too far into this. So the important thing for us is really just that the absorption is quite strong, totally contrary to europium-3+. And also due to emission being located here, it shows efficient energy transfer to europium-3+. So this energy transfer can be used to excite europium-3+. Also because the decay time of uranyl is quite long, the energy transfer is also efficient because there's sufficient time for the uranyl to do the energy transfer instead of emitting on its own. Also a nice thing is that both metals are in highest oxidation state, so you don't have problem with charge transfer, contrary to cerium-3+, where you can oxidize the cerium. Europium gets reduced, so this cannot happen here. So sort of a perfect pair. So this reflection spectrum here again shows how strongly it is absorbing in quite broad spectral region. So no matter which type of LED you choose, so either the conventional blue emitting LEDs, or which is becoming more typical recently, LEDs that are emitting around 400, 410 nanometers, uranyl is typically showing strong absorption in this region. And as you can see in this emission spectrum here, so we were exciting at 450 nanometers in this specific compound, and we only see really weak uranyl emission. So this is magnified by 100 times. So in the without magnification, you cannot really see the emission. It's down here, and all you find is europium-3+ emission. So all the energy is transferred from uranyl to europium-3+. So yeah, disadvantage of this specific compound is that it's showing relatively strong emission in the deep red spectral region around 700 nanometers. But yeah, we were just using this compound as an attempt to try and find out if the energy transfer is really working that well. So the reason why we were using this sort of strange compound is that it's comprising europium side and uranyl. So that's relatively rare that you have compounds where there's both a doping site for rare earth ion and uranyl cation in the same compound. Yeah, one question that of course always comes up is, if you use uranium, isn't that a big problem maybe? So a lot of people have strong feelings against uranium, but on the other hand, it's really not as dangerous and toxic as people often think of it. So phosphate-based fertilizers contain a lot of uranium actually, between 50 and 100 milligram per kilogram, so 50 to 100 ppm. And this is an example for Germany. Drinking water is allowed to comprise approximately 10 microgram of uranium per liter. So if you want to calculate in gallons, so that's 45 microgram. And if you drink a lot of water, like 10 liters a day, then that could amount of up to 7 milligram a year, and that's within the legal limits in Germany. So it's considered apparently not to be harmful. So the radioactivity is quite low. Even enriched uranium is not showing strong radioactivity. Surface of a container containing UF6, so enriched uranium hexafluoride, shows 4 microsievert per hour. And if you are traveling in a plane, so once that is allowed again, then you typically receive a higher dose even. So all that is left is a chemical toxicity of uranium, and that's comparable to that of cadmium. And quantum dots containing cadmium are quite widely used. So there's no real reason not to use uranium. Okay, a bit more information on this specific compound. So it's actually based on the mineral phosphorite. In nature, it's not containing a lot of europium, but rather yttrium and lanthanum. So we prepared this by a precipitation method, dissolving all the metals and precipitating with phosphoric acid. So then we receive a yellow precipitate that is showing quite nice emission. But the crystallinity is low due to the precipitation, and furthermore we have H2O in the structure. We also cannot get rid of it because then the structure breaks down. So the crystal is only stable if you have water, and water is quenching luminescence due to its high phonon energies. So basically it's a proof of principle, but not a useful phosphor. Anyway, we were doing some more investigation into this H2O problem of the phosphor, and we tried to substitute it with D2O, so that's deuterium oxide. The reason for this being that deuterium has a higher or larger mass than hydrogen, and therefore the phonon energies will be lower. And phonon energy, if it's high, then instead of emitting a photon, the phosphor can just emit or create a phonon or a vibration in the material. So as we hoped, the quenching decreases when we substitute H2O by D2O, but unfortunately it's not stable. So as soon as it's in contact with air, and in air you always have some amount of water as humidity, then the substitution will work backwards, and it will start to incorporate H2O again. So that you can see as the decreasing emission integral over here. Same shown in the spectra. So the spectra itself are not changing, but the intensity is changing as the powder is drying, and D2O is once again substituted by H2O in the material. So another europium phosphor that we came across is this potassium uranyl europium germanate. It has been published by some Chinese scientists, and they also reported on the luminescence properties, but not in detail because they were focusing on this new structure. So they are more a research group that is working with structural elucidation. So we prepared this compound ourselves, and the synthesis turned out to be somewhat tricky to end up with a really high quality powder. So I wrote it down here. It has to be reheated several times under oxygen so that you get rid of some oxygen defects. We suppose it's some reduction of uranium going on because you could perceive a slight greenish discoloration, and uranium 5+ is sort of typical for this type of discoloration. Another problem at lower annealing temperatures, we found this impurity phase, but finally we ended up with a nice high quality single phase powder. So here are the optical properties. You can see it's absorbing slightly less strong than this phosphate I was showing earlier, but it's still sufficient to use as an LED phosphor. So manganese 4+ in fluorides is approximately showing the same absorption strength as this material. And most importantly, when you excite it at 450 nanometers, so at 450 nanometers, europium 3+ has no transition, so you cannot excite it at that wavelength. We still found only europium 3+ emission and really weak uranyl emission. So even under 300 times digital magnification of this part of the spectrum, it's hardly visible. So quite lost in the noise of the background. So we ended up with what we wanted. So nice europium 3+ emission. And the excitation spectrum over here is showing that you can excite the europium 3+ emission over a broad wavelength range. Unfortunately, around 450, it's less good to be excited than in the UV region. This is due to the lower absorption in this part of the spectrum. But still, it is useful for LEDs that are emitting around 400, which I think are becoming more common nowadays. So one problem there is, unfortunately, in connection with this phosphor, it is showing relatively strong thermal quenching. So even at room temperature, or slightly above room temperature, it begins to quench. So on an LED, you will probably have a low quantum efficiency. So that, I have to be honest about it. That's really a problem with this phosphor. It's probably due to low-lying uranyl bands, and europium 3+ can then quench by relaxing via these uranyl bands. So it's sort of intrinsic to the phosphor. It cannot really be changed because we have these uranyl bands in the phosphor. If they wouldn't be there, then we couldn't excite it. So the energy distance between the 5D0 band of, or level, sorry, not band, of europium 3+ and the uranyl bands is approximately 5,000 wave number, and this corresponds sort of nicely to the thermal quenching activation energy. So we assume that is the reason for the quenching. So the question would be, is it possible to shift the uranyl bands to higher energy so that the distance becomes so large that it cannot be bridged? So far that unfortunately was not successful, and I have the suspicion that it's in this compound not possible to shift the bands that strongly. Last but not least, then we built an LED with this europium 3+ phosphor, blue LED, and fortunately it really was working, because in all our previous attempts, if you only use a small amount of europium phosphor as you would do in a commercial LED, typically you don't see any europium 3+ emission. In this case, we were really able to see europium 3+, so this is sort of exciting news. But of course, if the LED keeps running, heating up, then the europium 3+ emission will decrease due to thermal quenching. Still, the properties of this LED were quite nice. So we have a high color rendering index, around 86, can even be increased to 95 according to calculations. So for that, it would be necessary to really optimize the composition of the phosphor mix. So how much europium 3+ phosphor you're using, how much yaxerium you're using on the LED, and then you should be able to increase this really color rendering index to really high values of 95. At the same time, you have a really high luminous efficacy. So this is much more than in common commercial LEDs, which is just due to the fact that we have hardly any emission in this deep red spectral region. So this was the goal of the whole endeavor, to have red emission only in this region. So we have some around 700, but it's small enough, the lines, to not prevent a high luminous efficacy. So why were we not able to recreate this calculated values? I sort of said it before. It's probably due to the mixture, so this wasn't optimized down to a really fine level. Okay, one last interesting thing about this phosphor, it really shows a lot of europium-3 plus transitions. So usually what you can see are these well-known transitions, but if you were going ahead and measuring in this other spectral regions, but with a much higher sensitivity. So these values here are not digital magnification. So what we were doing is increasing the sensitivity of the spectrometer by using larger slit sizes and then just measuring this part. There you can really see nicely resolved line spectra of europium-3 plus. And they also show a really large splitting. So it's quite uncommon to find the 7F4 level spread over this large region from 690 to 710. Typically, it's a bit narrower. And we suppose this is due to the uranule in the structure. Then we also measured the decay time of the 5D0 sublevel, and we find similar trend to the emission integral. So this is typical if the quenching is via non-radiative relaxation from this state. So this also agrees well with the assumption that the uranule bands are responsible for the quenching of this level. And if you just measure time-resolved emission spectra of this one transition here. This is a 5D0 7F0 transition of europium-3 plus, which is always occurring around 580 nanometers. Here you can see a nice so-called rise time. So at after 5 microseconds after exciting the phosphor, the intensity is lower than after 20 microseconds. And this is once again a nice proof that energy transfer is going on because we are exciting the uranule, and it takes quite a long time to transfer all the energy to europium-3 plus. So after 20 microseconds, the intensity will have increased because during this time, the uranule was sort of transferring energy to the europium-3 plus. After that, the intensity is decreasing. This is then just the normal decay behavior of europium-3 plus. Okay, so in conclusion, uranule cation is a promising sensitizer for warm white LEDs if you want to use europium-3 plus. Of course, there are still some problems in relation with it. So people would still have to find a phosphor that is showing really high thermal quenching temperature, contrary to this germanate. Regarding the toxicity of uranium, I was mentioning this. It is a problem, of course, but we feel it's similar to that of cadmium, so it is manageable in my opinion. So we were able to fabricate really warm white emitting LEDs with europium-3 plus with high luminous efficacy, and the thermal quenching is an issue, and further investigation for that reason is required to end up with really high efficiency phosphors, but uranium could be a solution for this. Okay, this brings the talk to an end. So thank you, and if there are any questions, I would be happy to answer them.
Thank you very much, Professor Bor, for your very informative and nice presentation. I think sensitizing EU3 plus ion will help. It helps in using the efficiency of your phosphor and of course of that LED, and which are useful for warm light. I don't know how many people they have any or anybody is having any question, but I have one query for you. Are you listening?
Yeah.
So the this impurity exists in EU2 plus as well as 3 plus.
Yeah.
And in some of our phosphors, we found that there could be some change in their oxidation states. EU3 plus could change into 2 plus, and by exciting with some blue or UV light, or by annealing at high temperature and this thing. So the some fading or some of your phosphor or deterioration of your phosphor, is it related to such kind of redox reactions?
Yeah, you're right. So it could be a problem, but we hope that by annealing several times in pure oxygen atmosphere, that if there would be europium 2+, then it's oxidized to europium 3+. So I think it's often rather a problem if you have some other metals in there that are able to reduce europium, but the uranium is already oxidized. So yeah, it cannot reduce europium. So I think it shouldn't be a big problem here.
Suppose it takes some electron from somewhere.
Yeah.
Your processor is very complicated kind of system, more complicated system.
Yeah.
And it's reduced to, that can also a cause of deterioration. I don't know. I mean,
yeah, no,
I have not seen any. I have not seen any kind of pure spectral study in that region. I mean,
yeah.
Below this 450. So because UV2+ will appear around 420, 400, something like.
Yeah, that's actually a good idea. So we could try and excite this with UV or maybe even with X-rays. So with X-ray, then you should see everything that is in the phosphor. So yeah, that's true. That is an investigation that we could do. So I think we won't find europium 2+, but I don't know. So you could be right. It might be in there. Yeah, we didn't check this, and I also think if only exciting at 450, then we wouldn't see it. So yeah, we would really need to excite with high energy and find out if it's in there.
So it's really very interesting and exciting, your presentation.
Yeah, thank you.
Okay. Now we have another speaker of the session, Dr. Mamadou Aloma Dailo. Have you joined, sir? Okay. So I think there is some technical problem, and Dr. Diallo could not join at this moment. Maybe later.
Thermal justice.
So
This is the thermal justice.
over to the organizer.
Ritesh.
Yes, sir.
Over to Ritesh.
Who is the next?
Next is Professor Lauren Sendris from TC Turkey University is ready, I think. So shall we start this lecture?
Professor Banpurkar.
Okay. So before that, the chairperson for this technical session, because this talk is from technical session 4, is Dr. Arun Banpurkar, sir, Department of Physics, Savitribai Phule, Pune University. So I welcome Dr. Arun Banpurkar, sir, on this online platform to chair this technical session, and I request Dr. Arun Banpurkar, sir, to please conduct the session.
Hello, Ritesh.
Yes, sir.
I'm audible?
Yeah.
At the outset, I would like to thank Dr. Kokode sir and Dr. Sanjay Dhobde sir for giving me the.
Excuse me, sir. Kindly on the screen of Dr. Banpurkar, sir.
Yeah.
Post.
Yeah.
Dr. Erukude. Excuse me, sir.
What happened?
Banpurkar सरांना स्क्रीनवर घ्या.
हो.
Okay.
Yes, good.
Yeah. Thank you, sir. At the outset, I would like to thank Dr. Kokode sir and Dr. Sanjay Dhobde sir for giving me this opportunity to chair this session. This is a fourth session, but it is important session because both the speaker are from the electronic department, and electronics is required to drive the luminescence things. Okay, so the first speaker in this session is Dr. Kohran Sengiz. Dr. Kohran Sengiz is an assistant professor at the Department of Telecommunication, Trakia University, Turkey, and his area of specialization includes wireless sensor network, indoor positioning systems, routing protocols, MAC protocols, and spatial modulation, big data systems, NEMO systems, and wireless communication, including 5G networks. He is also expert in power electronics. In his credit, he has more than 20 publications, and he's young and dynamic researcher as well as engineer working in the field of networking and power engineering. I would like to invite Dr. Kohran to deliver his talk. Dr. Kohran.
Thank you very much. Can you hear me?
Yeah, sure.
Thanks a lot. I can share my screen for my presentation. Okay. Hang on a second.
Please share your screen.
Your screen is visible. Kindly open your presentation.
Yes.
Okay. Can you see now?
No.
Your screen is visible only.
You open your presentation.
Yes, this one. Can you see now?
No, sir.
Is it blue color screen is yours?
No.
I think the screen is frozen, so the mouse is not.
Screen is from dialog. Now it's
Visible.
Yeah.
Is it visible now?
Yeah.
Motivation.
Yes, you can see, right?
Yeah.
Right.
Okay, I'm starting, professors and researchers. Thank you for introducing me. I will shortly introduce myself. I'm Koran Cengiz. I'm coming from this presentation from Turkey. I'm assistant professor in Trakya University, Department of Telecommunications. It is a pleasure with you here today. My presentation will be about especially recent energy efficient studies for wireless sensor networks. This topic is highly related with my PhD studies, and in my PhD study, we aim to design an energy efficient, especially routing protocol for wireless sensor networks, and we aim to increase the especially lifetime of the network, and also we aim to provide significant energy efficient solutions for sensor networks. So as a motivation, in wireless sensor networks, there are a lot of usage places. For example, for disaster relief, target tracking, environmental control, smart cities, medicine and healthcare, we can use wireless sensor networks. And in a wireless sensor network, to distribute the sense data, in literature, we use especially three approaches. One of them is direct transmission, one of them is multi-op routing, and one of them is clustering. In direct transmission, each sensor individually collect the sense data from the environment. For example, we are making temperature measurements, and then the measured temperatures are directly sent to the base station. In multi-op routing, sensor nodes are used for relay nodes. They used themselves relaying the information from the network. And in clustering, they organized in a cluster by using predefined rules, and then cluster heads send the information to the base stations. So our studies are highly related with clustering protocols. We are studying in network layer, and we are trying to define and find new clustering protocols for network layer in wireless sensor networks. So, when we look at the literature, there are some common problems, especially for clustering. Especially three problems are foresight, increase in the energy consumption, decrease in the network lifetime, and additional network overhead. We are trying to solve these problems by using cluster topologies. And in clustering, especially most protocols use non-fixed clustering because they are trying to apply their environment and solutions to the mobile environment. So, for example, the best known clustering protocol is Leech, and it is used for mobile environments. But in our approaches, we defined fixed clustering approaches. So, Leech is very I saw some raising hands. Is there any problem or any question?
No, sir. No, sir.
Okay.
Question
Okay.
we can take it after the session.
Okay. Okay. Leech is the most known protocol, and it is designed for in 2000s, especially for mobile environments, and it has two phases. One of them is setup phase, and one of them is steady state phase. In the setup phase, the cluster formation occurs, and in the steady state phase, the data transmission in the distributed network are collected from the sensor nodes by using cluster head nodes, and then this collected information transmitted to the base station. So for each round, these processes are repeated in each protocol. So this provides and this brings a lot of network traffic in the network, and also for these messages, we use a lot of energy. In our approach, we thought that can we decrease this traffic, and can we decrease these message advertisements, these message transmissions. So then we thought that we can design a protocol which uses fixed clustering, and it can provide us additional energy savings. So also in literature, we have a lot of extensions to the Leech. When you look at the literature, you can find thousands of protocols, thousands of algorithms, but they are always focusing on three approaches mainly: changing the cluster selection, determining cluster heads according to the residual energies or remaining energies, and using fixed clustering. So therefore, we took from here this approach, and we said that we can use fixed clustering. And also there are some fixed clustering approaches also defined before in the literature. For example, LeechF is most known fixed clustering protocol. We also examined in details, and we found its some their deficiencies, and we tried to improve them. So also there are successful algorithm which is ModLeech, and it also provides additional energy savings to the existing approaches about Leech, but it still has some problems. And also DEEC is a most known another wireless sensor network protocol. It has some novelty in especially determining the cluster heads, because it uses a bound about energy level of the cluster heads, and according to this energy level, it determines the cluster heads. So all stable election protocol is very traditional protocol. It is used in the literature for many studies, and also many researchers made some improvements and enhancements to this protocol. Also, Lemma is another protocol. It is not very widely used. And also there are iLeach and pLeach. Let's talk about our protocol. Our designed networking protocol, especially it is a routing protocol in wireless sensor networks, has three main contributions to the existing approach. It aims to use fixed clustering and cluster head determination via base station approaches together. So it has two main ideas inside, using fixed clustering and also cluster head determination by using the base station, under control of base station. Also, it has an intelligent cluster head determination mechanism which tries to define the nodes that are almost at the center of their associated clusters at the beginning of the algorithm, instead of determining them randomly, because especially most protocols in wireless sensor networks define the cluster heads at the beginning, at the formation stage, randomly, but our proposed defines the cluster heads in a smart manner and tries to find the almost at the center of each cluster at the beginning. So at the beginning, it tries to increase the energy efficiency, and it tries to increase and also provides additional energy savings. Also, Lefka has a threshold-based cluster exchange mechanism, and especially this part is novelty of our approach. It aims to abuse the energies of the cluster heads before determining new cluster heads. So we saw that this idea is not proposed in any of the existing algorithms, and therefore, according to this approach, we published 3 SCI articles and 10 plus conference proceedings by using this novel approach. So Lefka again has 2 phases as in existing approaches. It has setup phase and steady state phase. In the setup phase, we made the cluster formations, and in the steady state phase, after the cluster formations, cluster heads collects information from the environment, from the sensor nodes, and then these cluster heads directly transmit the collected information to the base station. And the base station is outside of our sensor field. So its main job is collecting information from the sensor nodes, and the evaluations also about the information are done in the base station. So here also in details, the cluster head selection of Lefka is presented, and also these are our messages. In wireless environment, we use some messages, especially advertisement messages. For example, cluster head says to the members, I'm a cluster head, and also after that, members distribute information to the environment and the network that join request messages, and says that I'm trying to join your cluster. So therefore, we should use these messages in a wireless environment. So in clusters, for example, we have a cluster. It has a cluster head and it has 10 members in that cluster. Each member transmits its data in allocated time slot. So in an order. So for example, member 1 transmits its collected information from the environment in time slot 1. And for example, member 7 transmits its time slot 7. So then cluster head collect this information and it combine in a single message, and then it transmits to the base station. So when we transmit the information to the base station, our one round is complete. And the one round corresponds to collecting information from each member and sending this information to the base station via cluster head. So then, for the second round, same processes are repeated. And this is the steady state phase. In steady state phase, data transmission, as I mentioned before, is realized. So in data transmission, also cluster head collects information from the members, and then this information is transmitted to the base station, as we said before. Here is the novel part and a significant part of our proposed protocol. When data transmission is completed, the cluster head needs to decide whether it will continue as a cluster head for the next round or choose a new cluster. So how does a cluster head do this? So here, this decision is made based on the cluster head remaining energy. If the cluster head's remaining energy is above a predefined threshold value, it continues to act as cluster head for the next round. If, on the other hand, the cluster head's remaining energy is below the threshold, the current cluster head selects a new cluster head. The current cluster head chooses the new one randomly from the Li member of its cluster. This random selection is the original part of Lefka. In addition, we produced some extensions to Lefka, and also they were published in some conferences. For example, we made this selection selecting the member which has highest energy. This idea produced a new publication. In addition, for example, selecting the member which is closest to the current cluster head. This is also nearest fixed cluster head selection algorithm, NLEFKA, and also it produced another publication. So in addition, we have some new ideas about this part, and we are planning to apply these ideas to our upcoming publications. And determination of the threshold value is most significant step of Lefka, because the novelty is under this idea. So the threshold has a significant impact on the network lifetime. We obtained this result by our derivations and also detailed simulations. Also, we obtained the energy map of the network. I will show in the upcoming slides. So if the threshold value is very small, the cluster head might die. In network manner, we say that dying. So the cluster head might die during a round, and this causes to network disconnectivity. For example, imagine that you are using your wireless sensor network in a critical application, for example, fire rescue, earthquake measurement. So if you get network disconnectivity, you will lose the information from the network. So it will cause to critical problems in the measurement phase. So network connectivity is very significant for us in network engineering. So if we determine is very small, if we abuse the cluster head as much as possible, then for upcoming round or for next round, our cluster head can die. So if it dies, we cannot collect any information from that part of the network. So, for example, if there is a fire, we cannot be recognized. So it will be very critical and very bad situation for us. So if the threshold value is large, the algorithm might select a new cluster head for every round. So as you know, we said that existing approaches form cluster heads in each round. For example, Leach makes this. So we are trying to change this idea. So if we do this, then it will behave like Leach. So there is no novelty, and also there is no enhancement to the existing protocols. So we should define a threshold value very carefully, and we made some derivations, some mathematics to obtain the optimal value for this selection. And according to our, we started from the energy dissipation model in the wireless propagation channel. So we obtained that for our numerical values. For example, the worst case scenario, a cluster head, this is the this has the highest distance to the base station. For example, its coordinates has let's think 0, 0. For example, let's see from here. This is the worst case scenario. This is the worst cluster head, and it has very high distance to the base station, and therefore this cluster head approximately dissipates 0.0052 joules energy for a one round, for a single transmission, collecting the information from the network. And also it has 100 members. We calculated these values according to only one cluster, the worst case. So to provide connectivity, to provide exact survival, we decided that for our values, the threshold value can be 10 times, 10 times of this value, so it can be 0.05 joule. So we abuse the cluster head's energy until its value becomes 0.05 joule. And they started with 2 joules energy in the network. And from these equations, you can generalize for your cases. There is no problem. So we defined the threshold value according to these derivations and calculations. But here, for example, some researchers and some professors said before that this can be an energy hole here. You can have some problems. Also, in a lifetime manner, the first node that becomes very early. But for lifetime definitions, literature, we have 2 definitions in wireless sensor networks. First one is first node that, according to first node that, define the lifetime according to first node that, and also define the
Hello.
Huh?
Yeah, audible. Yeah. There is sound.
Yeah, you're audible.
Can you hear me?
Yeah.
Okay.
Yeah,
I'm
please
going
continue.
on.
Please.
Okay. So in the second lifetime metric, define the lifetime that all nodes become out of battery. So we selected that definition, and we said that our approach used this lifetime definition. So according to that lifetime definition, Lefka works successful. We will see in the results. And also we have another approach, which is Maltop Lefka. Let's summarize here to you. We also try to increase the performance of Lefka by using multi-hop solutions. And our Lefka, in our Lefka, for example, we have here cluster heads, and in original Lefka, for example, this is 5. Number 5 is a cluster head. It collects information from the members and it sends this information directly to the base station. But its duty is this. But in multi-hop Lefka, it sends the collected information to the neighbor relay node, and also this neighbor relay node collects the information for the upcoming cluster head, and then this upcoming cluster head, which is closest to the base station, transmits all collected information to the base station. So here, the only problem, there is a very huge network load in this node. But how can we solve this? This node, or for this cluster, the members can be selected can be selected supernodes. Also, there are some approaches in the literature. For example, these nodes can have 2 joules initial energy, but these nodes can have 5 joules, 10 joules initial energy. So then you can decrease the network load on this node. So also, this approach is published in IEEE Access Journal. It is our publication, another publication from this novel idea. And also it has same procedures as Lefka, because it is extension of Lefka, our design. And let's see some results about our simulations and analysis. First, we try to investigate the impact of number of clusters on the lifetime. These lifetime values are according to rounds. As you remember, 1 round is for us collecting the, first making the measurements and then sending these measurements to the cluster heads and sending this collected info to the base station. This is 1 round. So, for example, we have 100 sensor nodes in an area 100 meters times 100 meters. And for these values, under these parameters, our Lefka approximately survives for 5,000 rounds. This means we have 100 nodes, and when all of the nodes become out of battery, the system is closed. So here, these are the some results, especially for intelligent and random selections, and also, as you remember, for threshold value. This is the impact of threshold value. And also, this is the energy map of the network. We took some snapshots from the network. Different colors correspond to different energy values of the sensor nodes. Here also another energy map result. And this is the remaining energy. As you know, our 1 node has 2 joules, so we have 200 total energy, 200 joules total energy. And you see that Lefka has very scalable, robust behavior when we compare to other algorithms. It has a logarithmic behavior. And these are also our results, some commands. And here also shows we showed the number of alive nodes according to round number. So the problem is here, according to first definition, lifetime definition. Some professors said that first node that becomes very early because we abuse the cluster. This is the idea. But if we use the lifetime metric as all nodes die in the network, our approach becomes very successful. As you see, these are also some numerical results in a table. And here also, this was not our primary purpose, but after our evaluations, we obtained very significant results in our studies. So we obtained very significant performance improvement in data transmission to the base station because we can always collect information from the network, but some other protocols, there are some network connectivities. We also found out them. So here Lefka provides very large data transmission amount when we compare to other protocols. So this is also another novelty and very good performance improvement when we compare the existing approaches. Also, we looked at the performance of Lefka and multi-op Lefka for different node distributions, different dimensions. Again, when we increase the nodes, what's happening, the number of nodes. And also, this is the inside base station situation. When we put the base station inside, as you see, the performance of course increases because the distance decreases significantly. So also these are some results about multi-op Lefka and Lefka, our two approaches compared here. And these are also some numerical results in a table again. And with multi-op Lefka, we obtained not very much improvement, especially accordingly we obtained 5% improvements to the existing Lefka. We are still trying to increase the performance of multi-op Lefka nowadays. We have some studies about it, and these are the conclusions. As a conclusion, we propose to design a energy efficient novel protocol, especially for wireless sensor networks. And we aim to obtain especially full network connectivity and energy efficiency. Also, we aim to obtain significant increase in the number of data, amount of number of data transmitted to the base station. We obtained them successfully according to our studies. So here also for future directions, maybe we have some researchers here interested in this topic. Some machine learning and deep learning solutions can be applied to the clustering stage of Lefka. In addition, mobile base station solutions can be tried. Also, by using supernodes or hybrid cluster, hybrid environment, interesting solutions, interesting results can be obtained. And in addition, software-defined networking approaches and some Internet of Things-based solutions can apply to wireless sensor networks with Lefka, multi-op Lefka, and some new novel protocols existing in the literature. thank you for listening. Is there any questions I can answer right now?
Yeah, thank you, Koran. Yeah, if there are some questions, you can take some question.
Yes.
Is it any questions from the participant? Yeah. If there are no question, one question could be from my side.
Sure.
I think what could be the scenario in your let us say research related to 5G network?
To 5G network, especially for mobile environments, applying LEFCA or multi-op LEFCA can be a problem because, as you saw, that it is a fixed clustering approach.
Yeah.
But in 5G or 4G and future 6G networks, you know, users are all mobile.
Yeah.
So LEFCA can be modified to first mobile situations, and then it can be applied to 5G or mobile communications.
Yeah.
Also, we are trying to make some modifications about mobile cases because it is very significant nowadays.
Yeah.
You have a lot of heterogeneous networks.
Yeah.
In mobile networks, also Internet of Things based networks. So we will try to find some solutions to them.
Yeah, it's because of this pandemic situation and everything. All this network problem is now at a top priority. Thank you very much. Thank you very much for your nice presentation and all the informative discussion. Yeah, I think I would hand over this session to previous chairman because I think the participant from the speaker from previous session is present now. Dr. Sahare sir.
Yes, sir. Thank you, Banpurkar sir.
Yeah, thank you, sir.
Hello.
Hello.
Can you hear me?
Yeah.
Okay. Thank you, Sudhen sir. Hello.
Yes, hello.
Banpurkar sir, now thank you very much for your chairmanship. Now I request
thank you,
Professor P.D. Sahare sir, who is the chairman of our next session, and one of our yes, P.D. Sahare sir.
Previous session, he was chairman.
Professor P.D. Sahare is the chairman of our previous session, and the resource person of the previous session is Professor Mamadou Diallo, who is the founder and director of Carmel Research Institute, Africa. Hello, Atul. Atul, can you hear me?
Yes.
Okay. Am I audible?
Yeah, you are
Yes,
audible.
yes,
Your
Professor.
presentation is not audible, visible. Sorry.
No, I'm visible.
Kindly share your screen.
So, sorry, Dr. Banpurkar, for interrupting your session.
No problem, sir. Yeah, because this is nice thing.
One speaker
No
was
problem.
out over there, so I have to continue again.
Yeah.
So now I welcome Dr. Mamadou Aloma Diallo, and he's a electromechanical engineer and mathematical modeler. I'm surprised to see that he has masters in 3 subjects. He's a master's in 3 subjects and also doctorate. So he got his Doctor of Philosophy degree in 2019 in fluid mechanics and heat transfer from the University of Sheikh Anta Diop of Dakar, Senegal. And he is presently he has also is a member of London Mathematical Society, American Mathematical Society, American Society of Mathematical Engineering, and He also is on editorial board of Mathematical Modeling of Engineering Problems and International Journal of Heat and Technology, and is a director of Cornell's Research Institute, and he has also a lot of other publications and fields. So without wasting much time, let me invite Dr. Diallo to present his talk, his presentation. Thank you. Dr. Diallo, please.
Yes.
Yeah, please. You have 30 minutes for your presentation. Could you share your presentation desktop? Any technical problems, sir? Dr. Diallo, could you hear me?
Yes.
Yeah. So please.
You don't? Hello?
Yeah, you are.
Hi. Yes.
Kindly share your screen.
Yes. Do you see my screen?
No.
You don't see my screen?
No, not yet. We could not see.
Okay.
Yeah, now it is visible.
Okay.
Visible, it's fine now.
Go to your first slide, maybe. Yes.
Can't hear you.
Yes, go ahead, please.
Hello. Sir, no your sound now. You unmute yourself.
Yeah, please unmute yourself.
Hello?
Yes, it is.
Hello?
We could hear.
Do you see my screen?
Yes. Yes.
Please go ahead.
You don't see my screen?
Okay.
Yes. You don't you see my screen?
No, we could see your screen. Go to your presentation mode.
Screen is visible.
Go to full screen mode.
Yes. Oh, okay.
Otherwise, it's okay.
Yes, you start your now talk.
Please start.
So,
Could you listen to me? Please go ahead.
अरे अनम्यूट कर बरं त्यांना.
त्यांना अनम्यूट करा, त्यांना अनम्यूट करा एकदा. डायलो सरांना
अनम्यूट करा. अनम्यूट करा.
डायलो सर, can you hear me? Hello.
Yeah, I could hear, but ask Dr. Diallo whether he could hear me.
Diallo sir, can you hear me?
yes, I hear you.
Yeah, we could
Okay,
hear
just
you also. Okay, please go ahead.
Please go ahead.
Here's a sound.
Yes.
We could hear your sound.
Yes.
Go ahead.
बोला चिकटे सर. हो.
Diallo sir, we can't hear your voice. Hello, Diallo sir, please start your presentation.
Yes.
Please start your presentation, sir. Chairman is waiting. Chairman is waiting for you. Please start your presentation.
Yes. You don't see the presentation.
We see the presentation. We also hear you. So please go ahead.
You don't see the presentation.
We see your presentation. We also hear you. So no problem. Please go ahead.
But you have a sound. Do you hear the sound?
No sound problem. Please go ahead.
Do you hear the sound?
Yeah, we hear the sound. No problem.
So can I continue?
Yeah, please continue.
Continue, please.
Please give me just 1 minute. Just 1 minute.
Now it is clear and visible and audible, everything.
there any problem?
Hello, Professor Diallo.
Looks like he disappeared.
There seems to be some problem. Some technical problem, maybe internet problem.
Yeah.
Good morning, Ram sir.
Good morning. Good morning.
Yes, sir.
Good evening to you. I mean, good morning to me.
Yes, yes.
Sir, are you ready?
Yeah, I am ready. I can start any time.
Okay, so Banpurkar sir. Banpurkar sir. Hello. Banpurkar sir.
Yeah, I'm also ready.
So you start.
Yeah, they just announce from your side that we will be going to a fourth presentation or last presentation.
Kokode sir, shall I continue or you continue for the announcement?
Sir, you continue.
Okay. Now with the technical problem of from Mr. Diallo, I'm extremely sorry. Now I request to Professor Banpurkar sir to please start our next session, and the resource person for our next session is Professor Sriram Drujate from New York. So I request you, both of you, to please start the session. Professor Banpurkar sir.
Yeah, this is good morning, Ram sir. Yeah, because it could be 6:30 at your place.
Yeah, it's 6:50 at my my end.
Yeah. Okay. Dr. Sriram Durjate is president and owner of the Durjate Electronic Consultancy. Dr. Durjate held a senior position in engineering and research in medical system at Eastman Kodak Company, Analogic, and Bose Corporation before embarking on a career of full-time consultancy. Now he is a full-time consultant and president and owner of a Durjate Electronic Consultancy. He was educated at IIT Bombay and Yale University and has a degree in various fields, just like civil engineering, fluid mechanics, electronic instrumentation, especially biomedical engineering and control system theory. Over his career, he has designed medical systems such as patient monitors, defibrillators, CT scanners, fetal monitor system, digital and computed radiography, telemedicine, telehabitations, and precision analog circuitry for medical systems. He is a primary inventor of a retrofiable digital radiography systems. While at Kodak, this invention actually practically eliminates film in the radiography worldwide, and because of that, the portable radiography system is actually everywhere we can see. He wrote standards for AAMI on defibrillators and patient monitors. He does root cause analysis for medical devices failure, both for industry as well as for the US FDA. He has 16 patents in the area of medical devices and systems. He is passionate about affordable medical devices and design hand cranked defibrillators, which is very important in the medical field. He works closely with the Engineering World Health Organization, developing medical devices for underdeveloped countries, and is a member of the board of the Engineering World Health Organization. He consults power supplies for medical systems, X-ray generators, and sensitive analog electronics for medical devices. Dr. Ram is an experienced pilot. That's the important thing, and was a flight instructor. He is a live senior member of IEEE, member of SPI, member of AIMI, AAPM, and AHS. He is a distinguished lecturer for IEEE Consumer Electronics Society. He is a very senior professor, and all this, let us say, with all these capabilities in different field, I would like to invite Dr. Ram to deliver his lecture, because in this pandemic situation, this medical devices and medical field has a prominent importance, and which is driving the world now. Dr. Ram, sir.
Oh, thank you very much for your introduction.
Thank you, sir. Yeah, thank you.
Yeah, and I will share my screen.
Yes, sir.
And
yeah, just share the screen, sir. Yeah, sir. Yeah.
I'll go in full screen mode.
Yeah. Just go to the presentation mode.
Yeah, I'm going to the full screen mode. Okay, can everybody see my screen?
Yes, sir. Thank you.
Okay, I'll be talking about biocompatibilities of materials for medical devices. That's become very important today, because people are coming up with advanced materials and also 3D printing some of these materials. And what has been sometimes lost is people are not testing these materials to make sure that they're biocompatible with the application that they're using it for. For example, if you take ventilators and people are printing 3D valves, and those materials, unless they are biocompatible, can be toxic if we are not careful. So I'll be talking about methods of testing, and before that, I'll be talking about different parameters in biocompatibility. See, we define device biocompatibility as an interaction between medical device and tissues and physiological systems of the patient treated with the device. That is the FDA and ISO definition of what device biocompatibility is. So some of the factors affecting biocompatibility, I mean, these are the three major factors. There are other factors as well, but in a small presentation, it would be difficult to go and deal with everything except the more important ones. So the first factor is the chemical and physical nature of the components and materials, because we have to know what these materials are made up of, and we have to do chemical testing of these. And then the types of tissue that will be exposed to the device. For example, you could have, unbroken skin, in which case, I mean, for example, ECG electrodes, they are placed on unbroken skin. And then there are invasive systems like implanted systems, which actually contact the blood and bone, etc., etc. And also the duration of exposure, because as you expose these devices over time, as we'll see, chemicals can leach out of these devices and cause toxicity. So let's look at some of the parameters that affect these devices and the human patient. Okay, let's look at, first of all, how are we going to characterize the chemicals, because that's very important in new materials. And because older materials have already been characterized, and you can get the data from manufacturers, or if these materials are being used already, we don't have to characterize them, we just have to name them in our FDA submissions. So first of all, you determine the qualitative component of each material used in the device. For example, major components such as polymers, alloys, and metals, plasticizers, colorants, and antioxidants. These are added during fabrication, and some of these can be quite toxic. And then there are impurities such as unreacted monomers and oligomers, and manufacturing materials such as solvents and residues if they're not cleaned properly. Some of these materials might just stay with some of these manufacturing materials may stay with what you have manufactured. And then next, you estimate the potential for patient exposure for each item. And either you use the manufacturer's data sheets or you have to derive test data. So let's look at the nature of some of the interactions. Let's look at body contact for starters. You can have contact of less than 24 hours. For example, when somebody is taking an ECG or in a patient monitoring situation where the patient is not in the hospital or emergency room for over 24 hours, or greater than 24 hours when a patient is admitted, or permanent. Essentially, let's look at each of them. If you have surface devices that you could have contact on intact skin, mucosal membranes, basically, for example, if you have a ventilator, the intubating tube contacts mucosal membranes, or breached or compromised surfaces. Sometimes when somebody has injuries, it could be a breached surface. Then the external communicating devices include the blood path, which could be indirect, tissue, and bone or dentin, that is the teeth, and then circulating blood. And implanted devices, you could have tissue, bone implants, or, basically something that is in contact with the blood all the time, like an implantable pacemaker or defibrillator. So let's look at the test methods that we use in order to look for biocompatibility. Now, the first one is cytotoxicity. Usually that's done with tissue cultures. You evaluate using isolated cells in vitro, that is outside the body, and or you can do direct surface testing for low density materials. For example, if you're looking for long-term ECG electrodes, you can use that on the skin and look and see whether it's toxic, and usually that's done on animals before it's done on human beings. Then you have sensitization assays to determine chemicals that cause local adverse, local effects or systemic effects. Systemic effects include effects that happen throughout the body after repeated prolonged exposures. So, for example, you could do close patch tests for unbroken skin. And another thing is irritation tests, local irritation of skin or mucous membranes. And usually these are done on animal models because if you do it on people, could be dangerous because if somebody has allergies, you're likely to injure them. And then there's acute systemic toxicity because some of these chemicals would leach into the body after a while, and then at a certain point, their concentration increases in the bloodstream and the rest of the body, and they could be toxic to different organs, such as the liver, or kidney, or the heart. And then continuing on, there's genotoxicity that are in vitro and in vivo testing of substances that can cause genetic damage. And you have implantation tests, sutures, implantable devices such as pacemakers and defibrillators. And hemocompatibility is the next thing, where the devices that contact blood, such as intravenous catheters and hemodialysis sets. Thrombogenicity is very important because some of these chemicals can cause blood clots, in which case you could either end up with a heart attack or a stroke. Then we have to look at material and blood interactions. And carcinogenesis is something that takes a long time to determine, and usually it's a very controversial attribute, because that is looking at the tumorogenetic potential of the devices. Tumors take a long time to grow and become carcinogenic. And these are usually done in animal models over time. And the last one is reproductive and developmental toxicity. Essentially, these can affect the reproductive functions or unborn babies. So if you look at, so those are in general, many of the parameters that you look for. And usually these testings are done using, there's an ISO standard called 10993, that 2018 is the last printing of the standard. And the general, so essentially, if you look at it, this standard encompasses the general principles governing the biological evaluation of medical devices within a risk management process, because everything has a risk. In medical devices, we manage the risk by looking at it as low risk, medium risk, or high risk. If it's high risk, basically you don't use it. If it is low risk, there's no problem. If it's medium risk, we figure out how to manage it. So if you look at if you look at what this standard contains, it's the general categorization of medical devices based on the nature and duration of their contact with the body. And then, as I've said earlier, you evaluate existing and relevant data from all sources. For example, let's say you're building a new device and you're already using a valve or some component that's already been used, and you have FDA or CE identification for that. You can say so in your documentation, and you don't have to do new testing unless you're using it for a totally new application that wasn't used before. Then you identify some of the gaps that are in the available data, and then use that as a basis of a risk analysis. Then you have the identification of additional data sets necessary for analysis and the biological safety of the medical device. And the assessment of the biological safety of the medical device is done after that. And then if you look at, in summary, this document applies to evaluation of materials and medical devices that are expected to have direct or indirect contact with the patient's body during intended use, the user's body. Also, it's very important to look at what is happening to the operator, because, for example, there are certain chemicals that if the operator touches them without being careful, these are there in, for example, in chemotherapy, it's dangerous to the operator. And the users, that's why if the medical device is intended for protection, such as surgical gloves, masks, and others, PPEs today, because of the pandemic, are becoming very important. In fact, if you look at ventilators, the person on the ventilator may aerosolize some of the viruses, and one has to be careful not to breathe them in when you're treating this patient. So with that, I end my presentation. Any questions?
Hello, it's a nice presentation.
Hello?
Hello, Professor. Now are you ready?
Am I audible?
Yes, yes. Now I'm ready now.
Okay, okay. I just send you the message of the
Now,
picture.
Yes, yes.
You just
yes, yes.
Am I audible now?
Yes, yes.
Yeah.
Yes. So no problem.
Okay, okay. This presentation is over within 5 minutes. After that, we start your presentation.
Okay. Thank you very much. Thank you.
But Burga sir, you are audible.
Yeah. Sir, Ram sir.
Yes.
Yes. Could you like to suggest, for example, currently which some let us say polymers or some materials which is very commonly used in medical field, which is biocompatible?
Yeah, actually, one of the people have been doing 3D printing using filaments.
Yeah.
And some of the materials that are used, one of them is polymethyl methacrylate, PMMA.
PMM, yeah.
Which actually is also known as Perspex.
Yeah.
Yeah, PMMA is available in quite easily, and it is a biocompatible material because it's used in catheters, and it's used and is quite readily available. And there are other materials which people have. There's a I'll have to look up the
like PDMS. PDMS is polydimethyl siloxane.
Yes, PMMA.
No, sir.
Polymethyl methacrylate.
Yeah, the PMMA, also the PDMS, polydimethyl cyclogen.
Yeah, the one has to. I am not sure about that because there's the methylated compound in it.
Yeah.
And so you have to look at. You got to look at the bonding of the material and the leachability. But I have used PMMA quite a bit, and PMMA has been used in 3D printers. And there's a company. I'll look it up. Hang on 1 second. Let me go on my iPad, and I'll give you a link.
Yes, sir.
1 second.
Yes, sir.
I can actually, yes, 3D printing materials. There are some references. There's one can also do additive metallic printing.
Yes, sir. Yeah.
And why don't I send you references?
No problem, sir. Yes, sir. Yeah. But one question is there, because this PMMA is actually wettable, just like a Teflon is not wettable, but the PMMA is actually wettable to water and blood. Is it a problem in a biocompatibility?
Actually, fiber optic catheters are made with PMMA.
Okay. Yeah.
And you could put a shielding on them.
Okay.
But See, the other advantage of PMMA is its optical properties.
Yes, sir. Yeah.
You know, PMMA fiber optic material is one material that can handle both infrared and ultraviolet.
Yeah, yeah. Yes, sir.
And
It is
the
also
other
cheap
materials,
material. Yeah.
yeah,
It is not like Teflon. It is not that expensive as compared to Teflon.
yes, and there is a, I can, let me send you some of the references because right now,
No problem, sir. Yeah, I have your contact. So because I'm working in a soft condensed matter field, wetting, wettability, hydrophobic surfaces. So I would be interested in the biocompatible material and in possible uses in the biomedical field.
yeah,
Yeah.
because for example, you know, if you look at binding materials
Yeah.
for inkjet 3D printing, you have phosphoric acid, citric acid, PVA,
Yeah. Yeah.
and poly PDLLA.
Yeah.
And so, depending on the type of printing,
Yeah.
there are different materials. And essentially, in terms of many of the advanced materials,
Yes. Sir.
prototyping is often done with 3D printing. And therefore, you need to have materials that are biocompatible as well as 3D printable.
Yeah. Yeah.
I have used PMMA for parts for ventilators.
Oh, it's nice.
And that has not been a problem.
Yeah.
And as I said, I've used it in fiber optics. But obviously there are other materials, and there's a company that makes uh, um, filaments. Yeah, there are. Yes. I will send you the links to that, okay? Because I
No
don't
problem,
want to
sir.
take
Because
up
yeah, because
everybody's time
this is we
looking
are
up
in a session,
references.
so we can discuss in detail. One
Yeah.
important thing for a luminescence people, because as this PMMA is very let us say cheap, and it is actually biocompatible. So the luminescence people can add something like additives in this PMMA and can make a biocompatible let us say property or biocompatible devices. This is because the most of this community in this conference is from the luminescence property, and they are working in a mostly in luminescence field. So I think your lectures and your point of biocompatibility will be of added advantage to a kind of just like a bridging of the two field. I yeah, in that scenario, your lecture will be highly appreciated, and I thank you for your let us very nice presentation and overall the overview of this biocompatibility, because it's an important topic uh, along with the material property. Uh, Thank you, Professor Ram, sir.
Yeah, thank you very much for inviting me. And I know I had to do this a little earlier than.
Yeah, your busy schedule, from your schedule we have to.
Yeah, and then I'm seeing Mr. Diallo's presentation here.
Yeah, I think he might be joining after that.
And basically, Mr. Panse, I will send you some references.
Okay, sir.
Okay, sir.
So
Take all
that
this.
way, you could look at the other biocompatible materials, but one of the problems is some of these materials are so exotic, they may not readily be available in India.
Yeah.
Thank you again.
Okay, sir. Thank you very much. And I would like to thank both the speaker for their nice presentation and timely presentation and everything. Thank you very much, sir.
Okay. Thank you, Banpurkar sir. Thank you, Professor Ram sir. Thank you for your giving your valuable insights regarding biocompatibility, PMMA, insights on ICRTA 2020. Sir, I'm sure your valuable talk will help us in understanding the concept of recent trends in advanced material in future. Once again, I thank you, both of you, for your words of wisdom. It will be a great pleasure for us to listen you again in your future. Thank you, both of you, sir. Thank you.
Oh, you're very welcome. It's my pleasure to wake up in the morning and give a talk.
Okay, thank you. Now, our next speaker is Professor Diallo. So I request Professor P.D. Sahare, sir, as a chairman for his lecture.
So I'm already online.
Okay. Professor Yerpude. Professor Yerpude, please share the screen of Professor Diallo.
Yes.
Yes.
Yes. Do you hear me?
Yes.
Yeah.
Okay.
Welcome, Professor Diallo.
Yes.
Please go ahead.
Now, can I begin my lecture?
Yes. Please go ahead.
So, good afternoon, ladies and gentlemen. My name is Mamadou Diallo from Carmel Research Institute and Center of Advanced Computations. Today, we're going to talk about computational optimization in process heating. So we're going to follow this plan: introduction, overview of the solution method, modeling of the process, numerical solution of the direct problem, numerical solution to a heat transfer inverse problem, numerical solution to a heat transfer control problem, and last, conclusion. Process heating operations supplies thermal energy to transform materials like metal, plastic, rubber, limestone, glass, ceramics, and biomass into a wide variety of industrial and consumer goods. Industrial heating processes include drying, heat treating, curing, and forming, calcining, smelting, and other operations. Incremental technology advances have been achieved in the following areas: digital control equipment, reduction of emissions, increased thermal efficiency of selective processes, availability of high temperature materials, enhanced heat transfer, improved combustion system components. But here, we have to recognize that process heating is still very energy consuming. So here in this chart, we show that this process consumes much energy compared to other types of applications. Now we're going to talk about two systems: combustion-based process heating systems and electricity-based combustion heating systems. In combustion-based process heating systems, fuel in the form of natural gas, oil, coal, or waste products is combusted to generate heat, as shown here. For these fuel-fired systems, A key challenge is to optimize overall system thermal efficiency and operating costs while maintaining compliance with emission regulation resulting from the combustion processes. In electricity-based process heating technologies, an electric current is applied directly to material, or the electricity is used indirectly to power processes. Electricity-based process heating technologies include manufacturing for thermal processing, such as heating, melting, forming, curing, and drying. But here, for electrical systems, performance and cost depend on the reliability of the power supply. Opportunities to advance heat transfer technologies that might significantly improve their costs and performance includes the following areas. Uniform heat transfer. This can help reduce the cycle time, improve the quality of the goods, increase the productivity, and reduce the overall energy intensity of the process heating system. Second method is computational optimization of heat transfer. So we will focus mainly on this method, computational optimization of heat transfer. Computational models can be used to adjust variables of a model such as temperatures to determine the optimal condition for heat transfer, improving energy efficiency. And last, high-speed gas injection. In heat treatment furnaces, high-speed gas injectors can improve gas convection, resulting in more homogeneous temperature distributions and improved heat transfer. But in this talk, we're going to focus on computational optimization in process heating. The goal is we want to give to the heating processes the exact quantity of energy they need. And in the framework of this application, this is heat treatment of a steel in an electric furnace. In this application, we will use boundary temperature measurement for the control of process heating. So boundary temperature measurement. So we will use the following resolution method, which consists basically of 6 crucial steps. The first step is modeling of the heat transfer process. It consists mainly to determine the governing equations. The second step is the numerical solution of the problem. We have 3 methods of discretization. The first method is the finite difference discretization. The second method is finite volume discretization. And the third method is finite element discretization, which relies basically on what we call operational formulation. The third step is temperature measurement at the boundary of the heat body. So we're going to install sensors at the boundary of the body so that we know at each time the temperatures. And these temperatures will be our input for the computation of the radiative factor F by inverse methods. We can use optimization methods like conjugate gradient method, quasi-neutral method, steepest descent method. We can use genetic algorithm. And all these methods in order to perform the optimization and to obtain the factor F. The fifth step is the specification of the product required quality at the end of the heating process, T, because T is the depth of the heating process. So here we will go to specify the mean temperature at the time t and the standard deviation at the time t. All these two parameters are for the load. So we're going to specify the quality of the load we want at final time. And the sixth step is now, knowing the specifications, we can now compute the parameters theta 0, which is the furnace temperature, and the required time to achieve such a quality. For this, we can use Levenberg-Margat or other iterative regulation methods. So the first step is modeling the process. What is the problem? The problem is to find the equations that govern the heat transfer, governing equations. So here in the furnace, heat is transferred from the furnace to the load by radiation. And inside the load, heat is transferred by conduction. So the governing equation states this fact. The first equation of the governing equation is a diffusion equation. The second equation is the boundary condition. It states that the energy which is transferred by radiation is converted to a conductive energy inside the load. And the third equation is referred to as the initial condition. These three equations are called partial differential equation, where here U of x and t refers to the temperature inside the material at time t and location x. U0 is the initial temperature of the load. T is the duration of the heating process. Theta 0 is the source temperature. F is the radiative factor. K is the thermal conductivity. Cp is the specific heat, and rho is the density of the load. We can note that all the parameters K, Cp, and U, Cp, and rho depend on the temperature. Here in the boundary condition, we can see that we have the temperature to the fourth power. This fact makes that this partial differential equation is a nonlinear partial differential equation. So the second step is the numerical approximation. So here in this presentation, we'll use finite difference discretization. It consists of finding an approximation of the solution if U proves the grid, and here at each node, we have to find the approximation of the temperature by using finite difference discretization in 2 dimensions. So we can now perform simulation. 0, we can take it 20 degree. We have the furnace temperature, the time t, 2 hours, etc. And here we obtain the temperature distribution and the associated level curves. We can see that level curves are circles. We can see here that level curves are circles. And we can see here the value of each level. Now, we have to build the measurement temperatures. The measured temperatures are simulated using the exact value F bar of the F calculated with total zonal method. And then we add measurement errors modeled by a normal distribution with 0 mean and various standard deviations. This is the exact value of the factor F, calculated with the furnace parameters. And now, to simulate measurement, we have to add so a normal distributed variable with different level of measurement, with different level of standard deviations. So here, at each time, we compute the temperature for each standard deviation. And now this table gives us the measured temperatures in function of the time and in function of measurement errors. And this will be our input for computing the real value of F, what we will call F star. So here, for the inverse method, the problem is we want to find the factor F here in the governing equations, given experimental temperature data on the board here. So here we install sensors, temperature sensors, in order to know the temperature at the border. And based on these temperatures, we will use optimization and inverse methods to find this factor F. This problem is commonly referred to as inverse problem. This problem is commonly referred to as inverse problem. So what we have to do, we have to construct a function g of f, which measures the gap between the computed temperatures and the measured temperatures. And the value of f, the value we are looking for, will be this the values that we will corresponds to the minimum of the function g of f. So we are looking at this particular value of f, which we call f star. Termination here of the calculation occurs when the distance between two successive approximations of f, when the distance between these two successive approximations is less than the threshold that we have fixed in advance, delta. We can choose delta as 0.001, 0.002, or etc., or 0.005. It depends on the accuracy that we want. Here, now we can perform simulations. Here, we'll maintain the initial temperature. The functions K, Cp, and U are obtained with linear approximations. And we see here the curves corresponding to each method of optimization. Non-gradient optimization, gradient optimization, and quasi-neutral methods. We see here that our up to 0.006 is stable and very accurate, because we are not very far to 0.815. We are near 0.815. So the method is stable because we have not variation for different values of t up to 0.006, and the method is very precise. Now we shall tackle the control issue. We recall the governing equations. Now the problem is to find the furnace temperature theta 0 and the heating time T given desired quality requirement, U bar and sigma bar at the end of the heating time. The model gives us this function, which is the output of the model. Eta function of theta 0 and t. The first component of eta is the mean temperatures, and the second component of eta is the standard deviation. We want that this vector is the same as the vector u bar sigma bar. We want this relation to hold. We want that the vector here, which is at this side, be the same as the specification vector u bar sigma bar. This problem is commonly referred to as control problem because we want to find theta 0 and the time t. Here, this problem is particularly ill-posed. This is why we cannot use conventional methods like Newton method, collegiate gradient method, or methods like this. So here we are forced to use Levenberg-Margat methods. So here in the equation, mu is a positive scalar named damping parameter. D is a diagonal matrix. We can choose D as the identity matrix or D as GTG, where G is referred to as the Jacobian matrix of the vector function eta. The formula for obtaining G is this. We shall note that G is calculated numerically at each iteration step. Now we will treat two examples, two cases. For the first case, the heating time T is not known, and the surface temperature theta 0 is not known, but constant. And for the second case, the heating time T is known, but the surface temperature theta 0 is not known, but can vary according to a line curve. So this is the first case. The temperature of the furnace is constant. We have this specification, U bar and sigma bar. This is what we want. So here, after 10 iterations, we find that the furnace temperature is 500 degrees, and the heating time is 6.13 hours. So when the furnace temperature is at 500 degrees and at time 6.13 hours, we will reach the required specification, U bar and sigma bar. For the second case, the heating time is maintained constant. For the second case, the heating time T is maintained constant, and the furnace temperature will vary according to this law. That means according to a line curve. So we have to find the intercept and the slope. We maintain the same specification with the two subcases. We maintain the same specification. But here we have the time is very reduced. We have here 2 hours and here we have 4 hours. And we'll see what will occur in the computation. Here, if we compare the two curves, we note that when we reduce the time, the intercept here and the slope of the line curve will increase in absolute value. because we need the same quantity of energy in order to reach the goal. Here, for example, we must take a particular attention here at the beginning of the, because here we have a very important temperature gradient in the load. This can reach 150. So we have to ensure that the material can support this important temperature difference. Compared to the first case here, the gradient is not very important. So we have to pay particular attention to this fact. We have to ensure that the material can support this. If the material cannot support this important difference of temperature, we have not to reduce the time. We have not to reduce the time. So the choice of the time will depend on whether the material can support important gradient of temperature or not. So here, in conclusion, we can say that computational optimization in process heating contribute to the optimal use of electrical energy in the heat treatment processes, avoiding either wastage or poor quality of treated goods. Therefore, they participate in improving productivity in the industry. These are the reasons why computational optimization is crucial and foundational in modern engineering. Thank you very much.
Thank you very much, Dano, for your nice presentation. It was very informative. If anybody is having any question from the audience. If not, Dr. Dilo, I have a small query. Dr. Dilo?
Yes?
Yeah, I have a very small query. As you mentioned,
yes, you can.
Yeah, as you mentioned in the beginning, that this your simulation process or optimization could be used for combustion synthesis or combustion method also, because combustion synthesis is used in material science widely. So my question is, in the combustion synthesis, when there is a lot of gases are evolved, can still be such kind of simulations done?
Can you repeat the question, please?
In combustion synthesis or combustion process,
yes,
there will be some heat transfer, but as well as because the combustion is taking place, so a lot of gases are evolved.
Yes.
So your simulation process could your simulation process be applied to such kind of process also?
Yes, this simulation can apply to this kind. But here, the application was about an electric furnace.
Mm-hmm. There also,
so the application.
See, there also we can use the electric furnace, but in combustion process, the material is kept at some constant temperature, but at the same time when it starts burning, some gases are evolved. So I think the process could be, or simulation will be more complicated kind of thing, mathematical.
Yes. The process will be more complicated. Okay. Mainly when we try to model the radiation.
Okay.
Because the combustion gases will have an effect on the radiation.
Okay.
Yes. This is what they call participating medium. Okay. So the participating medium will have to be taken into account for this.
Okay. Thank you very much. Thank you once again. Over to the organizers. Thank you.
Thank you very much.
Thank you, sir.
Professor Vishal. So, on behalf of Dr. Vishal Panse, I thank both the chairmen for technical session 3 and 4. Professor P.D. Sahare sir, Department of Physics, Delhi University, and Dr. Arun Banpurkar sir, Department of Physics, Savitribai Phule, Pune University, for chairing the sessions and conducting the sessions. And I'm also thankful to all the speakers from technical session 3 and 4. As we are running on time, it's time to move towards the valedictory function. Before this, we will have a short video of valedictory function. I request Dr. Erkude to please play the video, and then we will have valedictory function. Dr. Atul. I think it is played from in between from the starting. Okay, shall we start? Okay, we will. Am I audible and visible?
Yeah.
So, shall we proceed towards valedictory function?
Yeah, no problem.
So, good evening, ladies and gentlemen. During this entire day, we have had insights into several issues on the advanced materials. We had dignitaries, participants, as well as the scholars from local, national, and international levels, enlightening us both in the theory and in practical ways to reflect philosophically on this area. Thank you very much to all of you. Ladies and gentlemen, to improve the golden moments of opportunity and catch the good that is in our reach is a great art of life. The galaxy of intellectuals, invited guests, professors, students, and ladies and gentlemen. I am Dr. Ritesh Kore from Department of Physics, Sant Gadge Maharaj Mahavidyalaya, Hingna. It is a matter of immense pride to be here before all of you this evening for valedictory function. So on behalf of organizing institutions, they are delighted to offer a gracious welcome to all of you. The fragrance of flowers spread only in the direction of wine, but the goodness of persons spread in their all directions. So we are delighted to have with us Dr. I.S. Morule sir, Registrar, Gondwana University, Gadchiroli, as Honorable Chief Guest of today's valedictory function. With an equal pleasure, we are also happy to have with us Honorable Dr. N.S. Kokode sir, Principal, NH College, Brahmapuri, as the chairman of this valedictory function. So on behalf of organizers, may I now request Dr. I.S. Morule sir, Registrar, Gondwana University, Gadchiroli, to please convey his valedictory remark to the august gathering. Please, sir, Dr. I.S. Morule sir.
Okay, thank you, sir. Am I audible? Hello? Am I audible?
Yes. Yes, sir.
Okay. Honorable Chairperson and Principal of NH College, Brahmapuri, my Guru Dr. N.S. Kokode, sir. Respected Principal of LBSA College, Sakharkeda, which is affiliated to Sant Gadge Baba Amravati University. Respected principal of Sant Gadge Maharaj Mahavidyalaya, Hingna Nagpur, affiliate to RTM Nagpur University. Convener of this conference, my friend Dr. Sanjay Dhobde sir. Organizing secretaries, Dr. Ghane sir, Dr. Mewade sir, Dr. Gawande madam, and Dr. Dhobde madam. And my dear fellow participants, good evening to all of you. I'm very much thankful to the organizers for giving me this opportunity to share my views with you on valedictory function of International Conference on recent trends in advanced materials. I'm also thankful to you all for your patience hearing. I hope you all enjoyed all the sessions deliberated in this conference. I also hope that you have decided to make your research career in the material science, because area selection is very important. If you are ready to do hard work, can make wonders in any area. I also attended all the sessions and listened all the talks excellently delivered by the respective research persons. They have elaborated excellently their topic. It's a great achievement for organizers for gathering 11 resource persons from all over the globe on a single platform. And the special thing is that all are from international level. All the resource persons having citation more than 11,000. It's a big achievement so far that I congratulate the organizers and wish in future to organize such type of great events with Scopus publications for the participants. Also, one thing which should be the most markable, that all the chairpersons of all sessions are renowned in the field of material science. My guru, Dr. Omanwar sir, my friend, Dr. Sanjay Dhobde sir, Professor Dr. Sahare sir, Professor Dr. Banpurkar sir, all are having great and remarkable work in their area. I advised to the new researcher in the field of material science, focus on quality work and try to publish the work in quality journals like Scopus, UGC Index, Thomson Reuters indexing journals, and try to establish their collaborations for development of research. I suggest them about hard work. Path of success is not easy nor swift. Everybody has to go through scratch. There is no magic which can make wonders in one night. We have to take efforts, planning, rigorous follow-up. Then and only then good things come up. If you have missed anything in life, don't fill your eyes with tears. It may hide yet another beautiful thing standing in front of you. Research should be your passion. Make research as your passion. Don't do it only to get certificate or good job or to get high API scores. Do it to make your career. Select only one topic. Go on doing it with new technologies forever. As technology changes, don't change your topic. Just modify your way of doing experiments as per new technology. Innovative ideas are always come in our mind when we are busy in some other international work, while traveling, reading, writing, cooking, etc., etc. Once the time passes, we hardly try to remember them. So be always with pocket diary with you. Whenever such innovations and dynamic thoughts came in your mind, just note down them. After that, whenever you will get free time, just revise them and try to add some more details. Do this exercise continuously. I'm sure at one day you will come up with wonderful and novel idea. Once again, I thanks to organizers and wish them to bright future. Thank you. Thank you.
Thank you very much, sir, for your words of wisdom. And really, we are really charmed by your well wishes. Well, your valuable guidance will definitely help us a lot in enhancing our future dimensions. So once again, thank you. Thank you so much, sir. Ladies and gentlemen, not a single event can be performed without a leader. It was a great opportunity for all teammates to perform under the able guidance of Honorable Dr. N.S. Kokude sir, Principal, NH College, Brahmapuri. Their efforts are marvelous and embark on new dimensions in the successful organization of this conference. He was really a driving force in organizing this huge conference in which we had a total 2,645 participants along with 11 international speakers. He really motivated us and stood full-heartedly behind us during the entire process of this conference. So not taking so much of your time, may we request Dr. N.S. Kokude sir on the online platform to deliver his valedictory remark. Please, sir.
Thank you. Thank you very much, Dr. Ritesh. Dr. Ishwar, guest of the function. I'm observing Professor Umanwa, Gahane, and they are sitting here. This is a very privilege and very proud moment for us. The international conference is successful now. Just now, it is reported 2,600 the eminent participants they have participated in the conference and around 11 international speakers. They delivered only two due to very good problems, timely problems. They were not able to deliver. But 9 international speakers they delivered. Now it is a very novel event that it was planned, and the whole credit goes to our chairman. So this is the very novel event that all the speakers they were from international, and chairman they were from this country, and particularly they were from the Vidarbha region. Dr. S.K. Omanwar, my friend, he has played this very novel idea, and Dr. Dobre has uplifted the same. Dr. Sanjeev Moril has supported all the way, and therefore this huge conference was successful. Almost all from USA, Africa, Turkey, Poland, Malaysia, Korea, Germany, and France. These eminent persons contributed from this country, and almost all the states of the India, the participants have already participated. This is a wonder idea that all the chairman, Dr. Doble, Dr. Omanwar, Dr. Banpurkar, and Dr. P.D. Shahare, all they have contributed a lot. Due to their active involvement in this conference, the conference is successful. And it is very pleasure for us, and it is very heart-touching moment for the Nevzabai Hitkarni College, Brahmapuri particularly, that Dr. Arun Banpurkar, Dr. I.S. Mohurle, Registrar, Dr. P.D. Shahare, all these, they are and Dr. Vishal Panse, Dr. D.S. Gahane, all are the alma mater of this college. And therefore, love and affection also made this conference successful. Dr. Dhoble and Dr. They help us in all the way. And because of these two persons, this conference has made this successful. And they acted as a chairman. So I am very much thankful to this all chairman, very, you can say, very intelligent persons, very hardworking persons, Dr. Omanwar and Dr. Dhoble, Dr. Shahare and Dr. Arun Banpur, big name in the country, who has dedicated their life for the luminescence, and many research papers they have contributed, many students. I will say that they have just made the generations of the scientists today. And it is very heartfelt moment for us that the Vice Chancellor of the Gondwana University, Dr. N.V. Kalyankar, who is also a student of physics, he also inaugurated this conference and given his blessing. Dr. KVR, senior person and president of the LSI, he has given the blessings and always stood up like a big support for us, and therefore this conference. And what is more important for us is that our grandfather, you can say, the main support for the Luminescence Society is Dr. Sanjeev Mohoril, who has given a very valuable and the remarkable, that is the motivation that he has introduced in the inauguration. That is the very generous moment for us, for the young people to look out this. I particularly very much, that is the very much thankful to Professor R.P. Rao, Professor Ravindra, Professor R.B. Pode, Professor Arup, Professor Marita, Professor Mikvita, Professor Diallo, Professor Justel, Professor Barr, Professor Senix, Professor Durjati, who has contributed. Only because of the illness, Professor Arup and Professor Justel could not make this their contribution in the last moment. But all these learned persons, they have given a nice talk, and our participants and young people will remember all the way their contribution in this conference. I will tell you that this conference was very, very successful because of the young, these our three persons from the three colleges, Dr. Atul Yerpude, Dr. Ritesh Kohole, they work day and night. They work day and night, and because of these three persons only, this huge, that is the conference, was successful, and all they have planned very nicely. Dr. Kohole, Dr. Vishal Panse, and Dr. Atul, they are just now the big scientists of tomorrow, I will say, that they have gained the momentum and they have arranged the things like anything. They have contributed a lot. So my personal blessing to this, all these young three peoples, and they're supported by their senior faculty members in these three colleges. So credit goes to all the three organizers, particularly our society members. They have supported us all the way. Dr. Moglewar, he is admitted in the hospital. Moglewar was their principal, and she has supported us like anything. Dr. Gawande, he was very busy, having the very busy schedule. Dr. Gawande, he left today itself to the Bombay, but he has given all the way, all the support to make this conference successful. So these three organizers, they work very hard and they have supported like anything, and therefore this conference was very, very successful. Now, behind this curtain, there are many things. The technical body from all the three colleges, they have contributed a lot. They have given a very strong support in all the three colleges: Gawande College, Sakar Kerda, Sant Gadge Maharaj College from the Hingna, their vice principal, their technical persons, their local organizing people. They have supported to Ritesh Kohole, they have supported to Vishal Panse, they have supported to Atul the Yerpude, the team from our college, Professor Thauri and their team, Dr. Pawar, Dr. Nagtode, Dr. Parshuramkar, Dr. Mungole, and Dr. Vakodikar, the technical committee, they have supported all the way for the day, and therefore morning 8:30 to now 6:30, they are working together. So all the technical committee in all the three colleges, they work day and night and made this conference successful. My thanks are also due to the advisory committee, local and national and international, that is the advisory committee. They have supported us. Many of them, they have given the guidance. They have made us the path very easy because of their experience. Many people phone us and give the guidance, and therefore this conference was successful. So I will say this was a very big festival for us. And in the course, due to the technical, sometimes we have all the three colleges face some difficulties because yesterday there was a heavy rain in Brahmapuri, also in Vidarbha region, and the internet problems, that was a very serious in this part of this. But I thanks particularly to the MSCDC, the electricity persons, and this BSNL. The engineer came here this site and throughout a whole day, the power supply and this internet facility was like last week, and I dedicate this conference, success of this conference, to all the young people who work for the success of the conference. Thank you very much. Thank you.
Thank you very much, sir. Really, we don't have words to thank you. It will not be completed by saying only thank you. So, thanks for sharing deep insights about this conference with us. I extend our sincere thanks for sharing your views that will really help us a lot in enhancing our further proceedings. Sir, it has been said that poor minds always discuss about the people's, average minds always discuss about the events, and strong minds always discuss about the ideas. And definitely today in this conference, we all have shared the innovative ideas, and it's all because of the mentors like you who standed behind us wholeheartedly so that we can follow your footsteps. So in future, we will try to enhance again the quality of the conferences and entire proceedings. Thank you. Thank you so much, sir. May I now request Dr. D.H. Gahane, sir, Vice Principal, NH College, Brahmapuri, to propose a formal vote of thanks of this valedictory function.
Thank you, Kovade sir. Good evening, everyone. I, Dr. D.H. Gahane, Vice Principal, NH College, Brahmapuri. At the outset, I pay my homage to former President of Neuzabai Bhaiya Hitkarini Education Society, Rashtrasant Tukudoji Maharaj, and late Madan Gopalji Bhaiya for his great love of education. Honorable guests, respected principals, teachers, researchers, and all my dear friends. It is my privilege to thank all those who have contributed towards this memorable event, International Conference on Recent Trends in Advanced Materials 2020, organized by Neuzabai Hitkarani College, Brahmapuri, led BS Arts, Professor NG Science, and AG Commerce College, Sakarkheda, Sri Sant Gadge Maharaj Mahavidyalaya, Hingna. For this memorable event, I would like to express my gratitude on behalf of all three colleges and organizing committee of the conference. I am grateful to chief patrons of the conference, Honorable Sri Ashok Ji Bhaiya, Secretary, Neuzabai Hitkarini Education Society, Brahmapuri, Honorable Dr. Nilesh N. Gawande, Chairman, Nehru Yuva Krida and Sanskritik Mandal, Chikli, Honorable Sri Uday Muglewar, Secretary, Basveshwar Education Society, Nagpur, for their inspiration and constant encouragement. Our hearty thanks to guest of inaugural function, inaugurator, Honorable Dr. N.V. Kalyankar sir, Vice Chancellor, Gundwana University, Gadchiroli,
Chairman of the function, Honorable Dr. KVR Murthy, President, LSI, MS University, Baroda. Chief guest, my Guru, Honorable Professor Dr. S.V. Moril, RTM Nagpur University, Nagpur. And guest of valedictory functions, Chairman, my Guru Dr. N.S. Kokode sir, Chief guest Dr. I.S. Mohurle, Registrar Gunwana University, Gadchiroli, who graced this occasion and address us my thanks to them. We express sincere thanks to all invited speakers, Professor R.P. Rao, USA, Professor Ravindra Pandey, USA, Professor R.B. Pode sir, South Korea, Professor Abdul Arab, Malaysia, Professor Marta, Poland, Professor Douglas Miktuja, France, Professor Diallo, Africa, Professor Thomas Justel, Germany, Professor Florin Bauer, Germany, Professor Orhan Cengiz, Turkey, and Professor Siram Durjati, USA, who graced this event with their valuable talk. We are equally grateful to Chairman of the Technical Sessions, Professor S.K. Omanwar sir, Amravati University, Professor S.J. Dhobde, RTM Nagpur University, Professor P.D. Sahare, Delhi University, Dr. Arun Banpurkar, Savitribai Phule, Pune University. Our thanks goes to our beloved principals of the colleges and organizers of this conference, Dr. N.S. Kokode sir, Principal, NH College Brahmapuri, Dr. N.N. Gawande sir, Principal, LBSC Sakarkheda, Dr. Arti Moglewar, Principal, Sant Gadge Maharaj Mahavidyalaya, Hingna, whose persistence, encouragement, and constant support made this achievement possible. Their love, foresight, and capacity lead us towards this goal. I express thanks to all conveners, Professor H.J. Dhobde sir, RTM Nagpur University, Dr. A.N. Erpude, NH College Brahmapuri, Dr. V.R. Panse, LBAC Sakarkheda, Dr. R.L. Ode, SGMM Hingna. My special thanks to Organizing Secretary Dr. Ganesh Mayawade, Vice Principal, SGMM Hingna, Dr. M.N. Gawande, LB SSC Sakarkheda, Dr. N.S. Dhobde, Sevadal Mahila College, Nagpur. Also all members of Advisory Committee, Mr. R.S. Mishram, Mr. R.S. Pashuramkar, and all members of Organizing Committee. Thanks to all, sir. On behalf of Organizing Committee of the conference, I express sincere thanks to all the participants from various parts of the globe, teachers, researchers, scholars, research scholars, students. I hope that this event will make the participants richer in the subject and they will carry sweet memories of this conference. My heartfelt thanks to all teaching and administrative staff of all three colleges for their endless, enduring hard work and cooperation in managing this event. At the last, but not least, I express thanks to technical committee members, Dr. Dhauri, Dr. Nagpure, Dr. Vakudikar, Dr. Pawar, Dr. Mungole, Dr. Tale, Dr. Nagmate, Mr. Kadbande, Mr. Madankar, Mr. Parikshit Walke. Finally, I express my sincere thanks to all those people who are directly or indirectly involved in the organization of this event. Thank you. What is it?
Over to Professor. Over to Professor.
I request all the participants to stand for national anthem.
भारत माता की
जय।
भारत माता की
जय।
भारत माता की
जय। Congratulations, Kokode sir. Congratulations to all.
Congratulations to you also, sir.
All new energy. Grand success.
Thank you.
Without any technical fault.
Congratulations, all of you, Professor Panse.
Same to you. डोबळे सर नमस्कार.
नमस्कार नमस्कार. काय म्हणता? चला अभिनंदन. तुम्ही बोलवा त्यावेळेस होतो.
आता सगळं ऑनलाईन सुरू झालं.
ऑनलाईन चहाची व्यवस्था झालेली आहे सर.
सगळ्यांनी ऑनलाईन चहा घेऊनच जावे. वर आणि वधू कडील पक्षांनी ऑनलाईन चहा घेऊन जावे.
सर छान झाली सर कॉन्फरन्स.
मोरले सर नमस्कार. हो मोरले साहेब.
हा नमस्कार जी नमस्कार.
रजिस्ट्रार साहेब आमच्याकडे लक्ष ठेवत चला.
अरे तुमचं लक्ष ठेवा आमच्याकडं.
चला अभिनंदन तुमचं.
आज मी दिवसभर ऐकले बरं कॉन्फरन्स. म्हणजे 9 वाजतापासून मी जॉईन केलेलं होतं घरच्या घरी.
घरपोच सेवा आहे सर.
हा घरपोच सेवा आहे सगळं.